Yes. So very good evening all. So in the yesterday session, we discussed about the types of the switches, the modeling of the switches, the numericals related to the conduction loss. Okay. And we introduced the composite switch. Now let us discuss some numericals related to the composite switch. So this is the multiple select type question. Multiple select type question means this type of questions they have added specifically in the GATE examination from GATE 2021 question paper. Okay, means latest question paper onwards. Multiple select question, the meaning is for the given question, okay, there will be the multiple options will be the answers. Okay, means if we are having the options as, let us consider this question. If we are having options as 1, 2, 3, 4, okay, so it is not like that only one answer will be correct. Okay, so multiple select means either the combination of any two options or three options will be there, right? So this is the MSQ, multiple select question. So let us first read this question. Yeah, I will explain the composite switch in this numerical itself. Okay. 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 Yes. So let us read this question. An electronic switch, yes, is required to block voltage of either polarity during its off state as shown in figure A. So here they have shown, right? Means the switch is required to block. The switch is required to block the voltage of either polarity. Either polarity means the switch is required to block the positive voltage as well as negative voltage during its off state. Okay, during its off state. So here we are having the plus, minus and minus plus, right? Means forward voltage as well as reverse voltage. This switch is required to conduct in only one direction during its on state, right? This switch is required to conduct in only one direction, means the it is expected that the switch should allow the current in only one direction during its on state as shown in figure B. Okay, so here they have shown. So allowed current direction is only from 1 to 1 dash during the on state of the switch, and it is expected that the switch should block the forward voltage as well as reverse voltage during its off state. So which of the following are valid realizations of the switch S? Okay, so our task is to find out of these four options, right, which options will fulfill the requirement, will fulfill the requirement. So let us first note the requirement. Here it is expected that during off state, it is expected that the switch should block the voltage of either polarity, right? Switch should block voltage of either polarity, that is positive as well as negative, or you can say the forward and reverse. Okay, voltage of either polarity. This is the one requirement. Second, during on state, it is expected that the switch should allow current in only one direction. Okay, switch should allow current in only one direction, right? So now here we are having the switch is 1 and 1 dash, these are the terminals of the switch, right? 1 and 1 dash, these are the terminals of the switch. Okay, so now from this given data, can we identify the type of the switch? Type of the switch means whether it is a unipolar, bipolar, unidirectional, bidirectional. Yes, can anyone? From the given data, can we identify the type of the switch, whether the switch is unipolar or bipolar? Yes, bipolar, na? Because during its off state, switch is required to block the voltage of either polarity, right? So it is here the, yes, let me write the bipolar. Given requirement is the switch is bipolar. And what about the unidirectional or bidirectional? As it is given that during the on state, switch should allow the current in only one direction, right? Direction. So that's why it is a unidirectional. Unidirection. It is a bipolar and unidirectional switch. Bipolar and unidirectional switch. So now can we find, can we identify the static operating point's location on the VI plane for our switch? Yes, we can. The switch is bipolar. Bipolar means it should block the forward voltage as well as reverse voltage. So the operating point should be here and here. Is this very clear? Right? This indicates the switch is blocking the forward voltage during its off state. Here, corresponding to this point, current is zero, na? So it indicates the switch is in an off state. Corresponding to this point, current is zero. So it indicates switch is in an off state. And what about the voltage across the switch? Voltage across switch is negative. Here, voltage across switch is positive. So it indicates switch is blocking the forward voltage. This point indicates switch is blocking the reverse voltage, that is the negative voltage, right? Next, as per the given data, the switch should allow current in only one direction, and that direction they have given, na? The direction is 1 to 1 dash. So that's why let us consider 1 to 1 dash current is nothing but a positive current. Okay, so that's why it is expected that the switch should allow the current in only one direction, that is a positive current, during its on state. During its on state, right? So now we need to identify out of these four options which switches, okay, fulfills this requirement, that is the blocking the voltage in either direction and yes, allowing the current in only one direction. So let us first check for the SCR. Let us check for the SCR. So first SCR for all the four switch combinations, I am going to draw the static operating points on the VI plane, and accordingly we will select which of these options are matching to the requirement. Okay, so let us first check for the SCR. So first is the SCR. Yes, it is given that this is a 1 here, this is a 1 dash here. Okay, now will you please let me know when SCR is in an off state? So this is voltage across SCR, this is the current flowing through the SCR. Okay, suppose the applied voltage is like plus here and minus here, means terminal 1 is positive, 1 dash is negative. So it is like we are maintaining the positive voltage across the SCR. Okay, we are maintaining the positive voltage across SCR. So suppose we are maintaining the positive voltage across SCR, but we have not applied the gate signal to the SCR. So what will happen? Whether our SCR will block that voltage or whether our SCR will start conduction. Yes, I am repeating. Suppose here we have applied the voltage such that terminal 1 is positive, terminal 1 dash is negative. Okay, and while identifying the location of static operating point on either plus V or the minus V, yes, recall the definition of unipolar and bipolar switch. In the unipolar or bipolar switch, which state we concentrate? We concentrate on, yes, blocking state. Okay, so suppose the voltage is positive, means plus here and minus here, but we have not applied the gate signal to the SCR, means our SCR is in an off state only. So therefore, whether our SCR will block that voltage, definitely our SCR will block that voltage. Okay, so here the operating point will be at this point. Okay, operating point will be here. Next, suppose same voltage plus here minus here, SCR is in a off state for this voltage. Now I am circulating the gate current. So what will happen? SCR is in a forward bias mode, and I am circulating the gate current in the gate cathode circuit of the SCR. Okay, So due to that, what will happen? Our SCR starts conduction. So when SCR starts conduction, in which direction the current will flow? Whether the current will flow from 1 to 1 dash or 1 dash to 1. Yes, for SCR, this is like anode, na? This is the cathode. So current will flow from, yes, anode to cathode means 1 to 1 dash, right? So that's why when the gate signal is applied, and by keeping this voltage polarity, that is plus here and minus here, means when voltage is positive, okay, and if we apply the gate signal, our SCR starts conduction. SCR starts conduction means current is flowing from 1 to 1 dash. So here current will be flowing from 1 to 1 dash. Okay, so that is the positive current. That is the positive current. Now suppose if we reverse the polarity of the voltage across the SCR. So reversing the polarity of the voltage across SCR means, let me write, yes, here it is minus, now here it is a plus and here it is a minus. Okay, now I am reversing the polarity of the voltage across SCR such that here it is plus and here it is minus. Okay, so if it is plus here and here it is minus, so it is like a cathode of SCR is at higher potential than that of the anode. So what will happen? Our SCR will be in the reverse bias mode. Okay, and when SCR is in a reverse bias mode, SCR will not conduct. Okay, we will discuss it while discussing the SCR again. Okay, in the SCR we are having 3 modes of operation. One is the forward blocking mode, second one is the forward conduction mode, and third one is the reverse blocking mode. Okay, so when voltage is negative, that is plus here and minus here, so SCR will be in the like reverse blocking mode. So SCR will not allow the reverse current, na? So that's why SCR will block that current. Okay, so the polar, yes, operating point will be here. So you can check SCR is blocking the forward voltage. SCR is blocking the reverse voltage during its off state. And here SCR is allowing the positive current during its on state. Right? SCR, yes, SCR doesn't allow the negative current. SCR allows only positive current. We have discussed SCR is a unidirectional switch. It is a bipolar switch. Okay. Is this clear? So this is the static operating point location on VI plane for the first option. Okay, that is for the SCR, right?
Hello, sir.
Yes, please.
Sir, your video is minimized. So
Video?
when I'm maximizing, your video is minimized. Could you do something about it?
My video is not visible.
Now it's visible. Now not visible.
Now it's visible.
Now it's visible.
Okay.
Could you keep that settings for the next ongoing classes?
Okay. Is it okay now?
Yeah, it's okay, sir.
Yes. Thank you. Yeah. So this is for the first option, right? So next, let us discuss for the second one. So this is the second combination we are having. It is a BJT now, and here it is a we are having the diode. Okay, it is connected just like in an anti-parallel. Okay, BJT and a diode. So let us check for this combination also. Second one. So BJT and diode. Right. So this type we are having, it is a 1, here it is a 1 dash. Okay. So now please recall the things about the BJT. Or for BJT, for MOSFET, and for IGBT, we have already drawn the static operating points on VI plane, and we indicated that BJT is a unipolar switch and unidirectional switch. It allows current in only one direction. Okay, and it blocks the voltage of only one polarity. Now, but here we don't have the BJT alone. Here we are having the BJT and the diode combination. So this is the composite switch. In the first option, it was only SCR. Okay, it was only SCR. So this is not the composite switch. Here we are having the composite switch here. This is the composite switch. Now here, suppose, yes, one is positive and 1 dash is negative. Means we are maintaining the positive voltage across the BJT. So positive voltage across BJT means plus here, minus here. Okay. So it is like a, we have maintained the positive voltage across the BJT, but suppose the base current we have not circulated. Okay, base current we have not circulated. So unless and until the base current is circulated, our BJT will be definitely in the off state only. Yes or no? Right? So can we say that when here it is plus, here it is minus, and if the BJT is in an off state, what will happen? Our BJT will definitely block this voltage. Yes or no? Right? Now let us check for the diode also. If here it is plus, here it is minus, the diode will be in the reverse bias mode. So whether the diode will allow the current in the reverse bias? No. Are you getting the point? Means try to understand, when here it is plus, here it is minus, and if the base current is not circulated into the BJT circuit, that is the base and emitter terminal, okay, base emitter circuit, then the BJT will block this voltage, and also the diode is in the reverse bias mode, so diode is also blocking that voltage. So overall switch combination, okay, overall as a composite switch, if you check, our composite switch is blocking that forward voltage. So how is the location of operating point on the VI plane? Yes, it will be like this. Here it is V, here it is a I, right? This one. What this indicates? Our composite switch is blocking the forward voltage. Is this clear? Next, let us check now. Suppose voltage is same, plus here, minus here. And now we are circulating the base current. We are circulating the base current through the base and emitter circuit of the BJT. So what will happen? Our BJT starts conduction. And definitely the current will flow through the BJT. Na? Diode will not allow the reverse current. But this BJT, once it turns on, this BJT will allow the current. So what is the direction of the current? Direction of the current is from 1 to 1 dash. Right? So 1 to 1 dash is the direction of the current, means where should be the location of the operating point? That should be on the plus I, na, right? So here it should be plus I. Right? Now let us check for the negative voltage. Let us check for the negative voltage. Negative voltage means suppose 1 dash is positive. Yes. 1 dash positive and 1 is negative. Okay. So 1 dash is positive and 1 is negative. So what will happen if 1 dash is positive and 1 is negative? Definitely our BJT, yes, will not allow the reverse current, right? In this direction, BJT will not allow the current. But what about the diode? Yes, can anyone? Diode will be in the forward bias mode, na? Because the anode of the diode will be at more potential than that of the cathode. So immediately, as soon as 1 dash is positive, 1 is negative, so diode will turn on. So when diode is turning on, so can we say that our switch is not blocking that voltage, that is the reverse voltage? Yes or no? But whether our switch is allowing the negative current, that is 1 dash to 1, yes, our switch is allowing the negative current. So that's why operating point will be here. Operating point will be here. Is this clear? Yes, Sai, do you want to say something? You have raised the hand. Dheeraj, Sai.
Hello, sir.
Yes, please.
Sir, just a doubt, sir. What do you mean by blocking here, actually, sir? Like, for instance, if this is operating as a switcher, the voltage you are applying across V1 dash, if it is positive, means VC is positive, no, sir?
Yes.
So only when a base signal is given, this thing will be on.
Only
when we like, अगर हम उस पर base signal डालें, तभी ये on हो जाएगा.
Yes. Blocking means what? The switch is in an off state. Okay. And we have applied the voltage across the switch. But as the switch is in an off state, so switch is not allowing the current to flow. Yes, that is nothing but the blocking the voltage.
Okay. So even if apply
suppose in your home, yes, we are having the electrical supply single phase, right?
Yes, sir.
And there we are having the switch, right? Okay. If that switch is in the off state, can we say that our switch is blocking that 230 volt? Yes, no?
Yes, sir.
Yes, in the same way. And when switch is in on state and if the appliance is connected, definitely that respective appliance will be the energizer, right? And we can say that the switch is in an on state and it is allowing the current.
Okay, sir. All right, sir.
Right?
Thank you.
Hello, sir.
Yes, please.
Sir, will you please explain this concept once again?
Okay, which concept?
Sir, about SCR and this diode.
Yes, this one, na?
Yes, sir. Yes, sir.
BJT and diode.
Yes, sir.
Okay. Yes. For BJT, here we are having the collector terminal, right? This is the emitter terminal, and here it is a base terminal, right?
Yes, sir.
Now, BJT is a current controlled device. Unless
Yes.
and until we circulate the base current here, the BJT will not turn on.
Okay.
First of all, we considered when the positive voltage is maintained across the switch. When the positive voltage is maintained across switch means here it is plus and here it is minus. Okay. And suppose now out of these two, if you check, BJT is an active switch because it is a controlled switch. Diode
Yes,
is a passive switch. Na? Diode is an uncontrolled switch. It is a passive switch. Diode will turn on immediately when it becomes forward bias, right? So now if you check here, suppose if BJT is in an off state, means we have not circulated the base current and we are maintaining this voltage. Now one is positive and one dash is negative, means what? For our composite switch, it is like a forward voltage is applied. Okay.
Okay.
Consider this full as a single switch. For a composite switch, the forward voltage is applied and we have not circulated the base current, yes, through the base emitter circuit of the BJT. So now what will happen due to this? As BJT is in an off state, so even though the voltage is plus here and minus here, BJT is in an off state means what? It is like a BJT is acting as an open circuit. So if BJT is acting as an open circuit, means current is not flowing. The meaning is, yes, current is not flowing. The meaning is our BJT is blocking that voltage.
Okay.
Are you getting the point? Right?
Yes,
Because
sir. Yes.
corresponding to the blocking, what is the current here? Corresponding to this blocking voltage, what is the current here? Current is zero, na?
Yes.
Right? So always keep it in mind. When the switch is in an off state and if the voltage is applied, the meaning is that switch is blocking that voltage. And
Okay.
Same thing I have already discussed. The voltage rating of a switch indicates the voltage, maximum voltage blocking capacity of that switch. For example, suppose if we are having a diode of, let us consider 800 volt voltage rating. The meaning is that diode can block maximum voltage of 800 volt. Okay, block, I am saying block. Okay, diode can block maximum of 800 volt voltage, right? Now, so this is the thing when one is positive, one dash is negative, and if the base current is not circulated, definitely the current will not flow because this BJT is in an off state, because BJT is an active switch, right? So therefore the yes, and what about the diode? If here it is plus, here it is minus, diode is in a reverse bias mode. So definitely this diode will not allow the current through it. The meaning is diode is also in an off state, BJT is also in an off state. So resultant overall as a composite switch, if we check, our composite switch is blocking this voltage, na? So that's why here it is a operating point at a plus V. Next, let
Okay,
us
sir.
check the voltage is plus here and minus here only. Now let us check voltage is positive only, plus here, minus here. And now I am circulating the base current. Okay, into the base terminal of the BJT. So due to that, what will happen? Our BJT will turn on. So as the BJT is turned on, once the BJT turns on, definitely the BJT will allow the current from 1 to 1 dash. And when the BJT is allowing the current from 1 to 1 dash, can we say that the voltage across the BJT terminals will be equal to 0? Because it is like a BJT is acting as a short circuit. And the current is flowing from 1 to 1 dash. So current is flowing from 1 to 1 dash. So that's why the operating point will be here. That is the positive current. Is this clear? Means the sequence is like, first of all, we need to consider voltage positive. We need to check whether the switch is blocking the voltage or not when your active switch is in an off state. Active switch means in this case it is a BJT. Second thing we need to check, if the base current is circulated by keeping the same voltage polarity. If the base current is circulated, that is nothing but our BJT will turn on. So once BJT turns on means BJT will allow the current, and that current direction is from 1 to 1 dash. So that's why the operating point will be here. Similarly, now let us check for opposite voltage, that is the negative voltage. Okay, negative voltage means it is like, yes, negative voltage means plus here and minus here. So suppose if I apply the voltage like 1 dash is positive and 1 is negative. If 1 dash is positive and 1 is negative, so what will happen? If you consider this switch, definitely this diode will be in the conduction mode, na? because when 1 dash is positive means diode's anode will be at a more potential, more positive than that of the cathode. So diode will be in the conduction mode. Okay, so as the diode is immediately switching into the conduction mode, can we say that when the voltage is like 1 dash is positive and 1 is negative, means when voltage is negative, our diode will allow the current in the negative direction. So overall our switch is allowing the current in the negative direction. That's why the here it is operating point. And now you can check whether our switch is blocking this voltage plus here minus here, whether our switch is blocking the negative voltage. No, because diode is an uncontrolled switch. Diode is a passive switch, and as soon as it becomes forward bias, our diode will turn on, right? So our overall, if you check overall as a composite switch, our composite switch will not block this negative voltage due to this diode here. Is this clear?
Okay, sir. Yeah, got it.
Yes, yes, yes.
Thank you, sir.
Okay, okay. So let us proceed. Now let us check for the third one. Next, third, we are having the option like, yes, this one, BJT and a diode in series we are having, right? BJT and a diode in series. Here it is BJT, here it is diode. Okay. So this is terminal 1 and here it is a 1 dash. Okay. Now, yes, please check when voltage is positive and if BJT is in an off state, means base current is not circulated, what will happen? Whether our switch will block that voltage or not. Come on. Suppose voltage is positive and we have not applied the base current to the BJT. That is like BJT will be in the off state. So when this BJT will be in the off state, na, so what will happen? Yes, our switch is not allowing the current, means what, the switch is blocking the voltage. Yes or no? Right? The switch is blocking the voltage. When someone is saying, students are saying it is not blocking. Why? I'm saying when base current is not circulated, so definitely it will be in the off state only, na? So that's why it will block the voltage. Diode is in a series with a BJT, but in a series combination, if you check, if BJT is in an off state, what will happen? The current will not flow, na? Current will not pass from 1 to 1 dash. So it is like switch is blocking the voltage, na? Right? So it is like switch will block the voltage. Right? Next, switch will block the positive voltage. Yes. Next, suppose the same voltage, that is a plus here minus here, and now I am circulating the base current. Now I am circulating the base current. So once the base current circulated, the BJT turns on. So when BJT turns on, whether the current will be flowing from 1 to 1 dash. If BJT is turned on, whether the current will flow from 1 to 1 dash, definitely na current will flow, because diode is an uncontrolled switch. And if it is plus, if it is minus, and if the BJT is in an on state, definitely diode will be in the on state only. So that's why current will flow from 1 to 1 dash. So it is a operating point. Now let us check for the negative voltage. Let us check for the negative voltage. Negative voltage means, yes, it is like a plus here and minus here. So now can you tell me for the negative voltage, what will happen to this diode? If 1 dash is positive and 1 is negative, it is like a cathode of a diode will be more positive. Okay. So diode will be in the reverse bias mode. So if the diode is in a reverse bias mode, whether the current will flow from 1 dash to 1? No, means our overall switch, okay, is blocking that negative voltage. So operating point will be here. Yes or no? And now whether due to this diode, whether the negative current will be flowing, negative current means this current. Whether the negative current will flow? No. So that's why operating point will not be here on the minus I. Operating point will be only on plus V, minus V, and the plus I only. Keep it in mind while finding these points. That is the while locating the operating points on the plus V or the minus V. We need to think about the active switch is in a off state, because the definition is unipolar and bipolar definition. Na? In that only we have discussed while finding the unipolar or bipolar, we need to consider, we need to focus on off state of the switch. Yes or no? Right? And while checking for, yes, or unidirectional or bidirectional, we need to, yes, concentrate on state or the conduction state of that active switch actually. Okay, because passive switches are the uncontrolled switch, not diode is uncontrolled switch. Okay, so is this clear? So this is the these are the operating points. Next, let us check for the fourth one. Okay, fourth is a combination of, yes, this one, third, and the, yes, again diode is connected in anti-parallel. Please don't raise the hand. We will discuss all your doubts at the end of the session. Okay. So fourth one. Yes, it is like this. This is a 1, this is a 1 dash, right? This is a BJT, and here it is diode and diode. Now, what about the plus V, whether the switch will block the voltage or not? Yes, this is the V, this is the I. Come on. Yes, suppose here it is a plus, here it is a minus. Okay. And if this BJT is in a off state, BJT is in a off state, means base current is not circulated. Okay. So whether the current will flow into this branch, right? No, current will not flow here. Whether the current will flow through this diode? No, because diode will be in the reverse bias mode now, right? So this diode is blocking this voltage, positive voltage. At the same time, when BJT is in a off state, yes, our BJT is also blocking that voltage. So that's why the operating point will be here, right? So it is like our composite switch is blocking the forward voltage. Let us check. Now voltage is plus here, minus here only. But suppose if the gate, so if the base current is circulated into the BJT circuit, if the base current is circulated into the BJT circuit, what will happen? BJT will turn on. Once the BJT turns on, the current will be flowing from 1 to 1 dash, because this diode will be in the on state only. Okay. So that's why current will be flowing from 1 to 1 dash, right? So current is flowing, that is positive current is allowed, will be flowing through the switch. Next, let us check for the negative voltage. Let us check for the negative voltage. Negative voltage means, yes, it is like a plus here and minus here. Now here it is plus, here it is minus. What will happen? Whether our this diode will be in the conduction mode or it will be in the off state. If the voltage is plus here and minus here, definitely this diode will be in the conduction mode. So if this diode is in the conduction mode, so diode immediately starts conduction. So that's why the reverse current will flow. Now reverse current means 1 dash to 1, I am saying. Okay, so reverse current is allowed. Means what? Reverse current will flow. And what about the reverse voltage? Immediately the reverse voltage is applied, that is 1 dash is positive and 1 is negative. As this diode is in the conduction mode now, so that's why we can say that our composite switch is not blocking that reverse voltage. So that's why the operating point will not be here, right? So operating point will be here only. Okay. So now we can check for all the 4 options. We are having the locations of the static operating points. And what is our requirement? Our requirement is, it is like a, yes, bipolar and unidirectional. So you can check the options, bipolar, unidirectional. So first one is the matching, right? What about the second one? Second one is not matching, right? Not fulfilling the requirement. Third one, yes, third one is also fulfilling the requirement. So correct options are 1 and 3. So that's why it is a MSQ type question, multiple select type question. Are you getting the point, right? Fourth one is not fulfilling the requirement. Okay. Is this clear? Next, let us discuss next example. Okay. Yeah. Now what about this one? Same options as that of the previous case, but the question is changed here. An electronic switch is required to block only one polarity voltage during its off state. It is given that only one polarity voltage is required to block. okay, and allow current in both the directions. Okay, it is expected to allow the current in only one direction, in both the directions during its on state. Okay, so here it is a on state and here it is a off state. Which of the following are valid realizations of the switch? Yes. Now, if you check the requirement, so from this, can we say that yes, it is like an electronic switch is required to block any one polarity, means what? Either positive voltage or negative voltage. So it is a unipolar, and it should allow the current in both the directions. So that's why it is a bidirectional. So it is a unipolar and bidirectional switch. We need to identify from these options. Are you getting the point? Unipolar and bidirectional. So for unipolar and bidirectional switch, what will be the possible combinations of static operating point locations on VI plane? Yes, unipolar and bidirectional. Bidirectional means positive current as well as negative current. So bidirectional means here it is as well as here it is. Operating point should be there. And unipolar means, suppose if I put here, then in the second one, yes, switch should block either positive voltage or negative voltage. Now here I have shown switch is blocking the positive voltage. Now in this case, I will show it is blocking the negative voltage. So now for all these four options, just now we have drawn the static operating point locations on the VI plane. We need to check which of those options are matching either this one or this one. Are you getting the point? Because it is given that an electronic switch is required to block only one polarity voltage during its off state, but they have not mentioned the which polarity voltage. Only one means the voltage will be either positive or negative, na? Yes or no, right? So we need to check out of these four, whatever the those static we have operating points on VI plane we have drawn. So from that we need to check which switch combinations or which options are fulfilling either this one or this one, right? And that will be our answer. Okay, so you can check here either this one or this one means you can check here. Yes, both the directions current. Okay, so first is not allowing the current in the both direction. Okay, so first is not there. What about the second? Allowing the current in both the directions and blocking the positive voltage. So that's why the second will be the yes correct option. What about the third one? Third is not there, right? It is bipolar and unidirectional, but we require unipolar and bidirectional. Okay, next you can check for the fourth one. It is also blocking the forward voltage and allowing the current. So first and the fourth. Are you getting the point? So correct options are first and the fourth. Is this clear? Right? So first and the fourth. These are the correct options. Okay. Next. Yeah, let us check for this one. I'm expecting the answer from you for this question. Draw steady state operating points for composite switch shown in figure. So this is the composite switch. It is a combination of thyristor and 4 diodes. Okay, across A and B we are having. Suppose, yeah. This is a V, this is a I. Suppose operating point here is a, operating point here is a B, operating point here is a C, operating point here is a D. Now, will you please let me know, yes, for this composite switch, for these composite switches, out of these 4, A, B, C, D, okay, where will be the static operating point locations? Check for positive voltage. Initially consider the active switch is in an off state. You can check whether the switch will block the voltage or not. Next, same voltage plus, here it is plus, here it is minus. Circulate the gate current through the thyristor. Check whether the current will flow from A to B or not. Next, reverse the polarity, that is a B plus and A minus, right? B positive and A negative. Yes, don't circulate the gate current, that is keep the active switch in an off state and check whether our composite switch will block that voltage or not. And in the last case, same voltage, that is a B positive and A negative. And next, circulate the gate current through the thyristor gate cathode circuitry, so that thyristor will be in the on state. And please check whether the current is flowing from B to A or not. Here voltage positive means A is positive, B is negative. Voltage negative means B is negative, A is positive. Current positive means current is flowing from A to B. Current negative means current is flowing from B to A. Come on. 4 diodes we are having, and diodes are the uncontrolled switches, right? The BJT during the negative voltage, what will happen, that you will understand while discussing the BJT. Okay. Some are saying 2 and 4, and some are saying all the 4. Okay, let us discuss. Okay. So suppose A is positive and B is negative. A is positive and B is negative. So what will happen? Initially, suppose active switch, that is a thyristor, is in a off state. Okay. And we have applied the positive terminal, yes, positive polarity voltage here and the negative voltage here, right? Next. So as thyristor is in a off state, here it is plus, here it is minus. So it is like a higher potential will appear at the diode D1's anode. Okay. Higher potential will appear at the diode D4's cathode. So what will happen? The higher potential is appearing at the diode D1's anode, higher potential is appearing at the diode D4 cathode. So can we say that diode D1 is in a forward bias mode? Diode D4 is in a reverse bias mode because cathode potential is more, na? So diode D4 will be in the reverse bias mode. D1 forward bias mode, D4 reverse bias mode. Similarly, this is a negative. So this negative will appear here and same negative will appear here. So you can check here for diode D3, the anode potential is lesser, and for diode D2, the cathode potential is lesser. So you can check here, as the anode potential is lesser, the meaning is the diode D3 is in a reverse bias mode. Diode D2, cathode potential is lesser, the meaning is diode D2 will be in the forward bias mode. But even though D1 and D2 are in a forward bias mode, for this voltage plus here and minus here, but thyristor TH is not turned on. So whether the current will flow from A, D1, thyristor, D2 and B? No, because main switch is in an off state. So the meaning is, can we say that if thyristor is in an off state and if A is positive and B is negative, that is the voltage is positive, can we say that our switch will block that voltage? Yes. So operating point will be here, that is a A. Now suppose for the same voltage, that is a plus here and minus here, now I am applying the gate pulse to the thyristor. So what will happen? As soon as the gate pulse is applied, thyristor will turn on. So once the thyristor turns on, current will flow from A, D1, thyristor, D2 and again back to the B. Yes or no? In this loop, definitely the current will flow. So as the current is flowing into this loop, yes. So can we say that this current is positive or negative? Current is flowing from A to B. So that's why current is positive. So that's why this will be our operating point. Okay. Next, let us check for the negative voltage. Now, negative voltage means A is negative and B is positive. Right? So A is a negative and B is a positive, right? A negative, B positive. So what will happen? This plus will appear here and here. This minus will appear here and here. What about the diode D1? Forward or reverse bias? Anode is at lesser potential. So diode D1 reverse bias. Diode D4 forward bias. What about the diode D3? Anode is more potential, more positive. So that's why D3 forward bias. Diode D2 reverse bias. This plus, no, sorry, this here should be plus. So diode D2 reverse bias. So here D3, D4 forward bias, D1, D2 reverse bias. Suppose voltage is plus here, minus here. We have not applied the gate signal to the thyristor. So thyristor will be in the off state. So if thyristor is in off state, whether the current will flow from B to the A? No, even though D3, D4 are in a on state, but in a forward bias mode, but main switch, that is the thyristor, is in a off state now. So that's why current is not getting the path. Okay, closed up path here. Current is not getting the closed up path. So that's why our switch will block that negative voltage. So this will be the operating point. Now let us check for the, yes, when the gate pulse is applied to the thyristor, then what will happen? Same voltage plus here minus here, and if the gate pulse is applied to the thyristor, so our thyristor will turn on. So once thyristor turns on, current will flow from B, D3, thyristor, D4, and again back to the A. In this loop, the current will flow. So if the current is flowing into this loop, can we say that this current direction is from B to A? So current direction is from B to A means what? The current is negative. So our switch will allow the negative current, right? So therefore point D will be the, yes, operating point. So all these four are the operating points. So can we say that, yes, this is the bipolar bidirectional switch, right? So bipolar bidirectional switch. Bipolar bidirectional switch, right? So please follow the procedure. The procedure is like, first of all, maintain the positive voltage. It may be 1, 1 dash, maybe A and B, etc. Okay. So maintain the positive voltage. Keep the active switch in an off state. Check whether the current will flow or not. If current is not flowing, it is like our switch is blocking that voltage. This is the first case. In order to identify this point, Second case, keep the voltage same positive, right? That is A positive, B negative, or 1 positive, 1 dash negative, etc. Anything you can say. And turn on the active switch. I'm saying active switch. Turn on the active switch. If the BJT is there, it is like a circulate the base current. If the thyristor is there, it is like a circulate the gate current. Okay, like this. If the MOSFET is there, it is like a circulate the apply the VGS voltage. Okay. So second case is same voltage positive and active switch is turned on. If the active switch is turned on, please check whether the current will flow from A to B or not. If current will flow, then the operating point will be at this point. Okay, that is like our switch is allowing the positive current. Third step is that reverse the voltage, means it is like B positive, A negative, or you can say in general 1 dash positive and 1 negative. If 1 dash positive, 1 negative, in that case, first again, what we need to do? We need to keep the active switch in an off state. Once the active switch is in an off state, we need to check whether the voltage will be blocked by our circuit, by our switch or not. Okay, voltage blocked means what? If the current is not flowing, okay, from B to A, the meaning is our switch is blocking that voltage. Okay, so it indicates this point. Okay, and last one is the same voltage, that is the B positive, A negative. Now turn on the active switch. If the active switch is turned on and if B is positive and A is negative, then we need to check whether the reverse current will flow or not. If the reverse current, that is the B to A current, will be flowing, then the operating point will be here. Otherwise, it will not be here. Right? So follow these 4 steps. That's it. Okay. Next. Yeah. One more question. This is from gate 2003. Okay, gate 2003. It is a MOSFET with a body diode. Yesterday we discussed this. Yesterday I have given MOSFET with body diode, right? So now for the MOSFET alone, I am saying, okay, for the MOSFET alone, how is the static operating point on VI plane location? It is like a positive voltage and the positive current, right? Positive voltage is blocked by the MOSFET during its off state, and positive current is allowed by the MOSFET during its on state. Now here the diode is connected. So let us discuss one by one. Suppose this is the voltage. They have given VDS. So let me write it as a VDS. And here it is a IS. Let me write it as a IS. Okay. VDS and IS. VDS and IS. Okay. So now check. Okay. On and off states of the switch are given on the VDS IS plane. Okay. Okay. Now we need to check. Yes, if VDS positive means here it is plus and here it is minus. First step is positive voltage, but gate and source voltage is not maintained across the MOSFET. So our MOSFET will be in the off state. So if voltage is plus here, minus here, and if the MOSFET is in an off state, what will happen? Whether the current will flow from drain to source? No, because this diode will not allow the current, and at the same time MOSFET is also in the off state now. So that's why drain to source current will not flow. Is this clear? So that's why our switch will block the voltage. Now check again, same voltage polarity plus minus. Now we are maintaining the gate to source voltage. Now we are maintaining the gate to source voltage, so that MOSFET will turn on, because here active switch is MOSFET na. So MOSFET has turned on. So if the MOSFET is turned on, what will happen? From drain to source, current will flow. If the current is flowing, so positive current na, drain to source, they have given current direction IS here. It is in the downward direction. Okay, so this is a positive current is flowing through the switch. Let us check for the negative voltage. Negative voltage means it is like a drain is at a lesser potential and source is at a more potential, right? So here it is plus, here it is minus. So if here it is plus, here it is minus, what will happen? This diode will start conduction immediately, na? So once voltage is plus here, minus here, this diode starts conduction. So reverse current will be flowing. Reverse current will flow. But whether this diode, due to when the diode is in the conduction mode, can we say that our switch is not blocking the reverse voltage? Because as soon as the reverse voltage is appear across the composite switch, that is like this will be the forward voltage for diode. Plus here, minus here, it is like a forward voltage for the diode, and diode will start immediately conduction. So that's why operating point will not be here on the minus V axis. Please be careful. So operating points will be here only 1, 2, and 3. So if you check the options, yes, correct option will be, yeah, option B is the correct option, right? 1, 2, and 3. Okay. Next. Yeah. This is the one question from GATE 2014. Okay. This will be the homework for you. Please try to simplify it. We're having the 4 switch combinations, right? One is the IGBT and the diode. IGBT blocks the forward voltage. IGBT alone, I am saying. Okay, it blocks the forward voltage and allows the forward current. Okay. Thyristor, we know it is the bipolar and the unidirectional switch. Okay, and we're having the combinations like this. Check for this. Okay. Yeah. So now let us move towards the next point. Yes, the next one is the now we are actually moving towards whatever till now we have discussed. It was like general concepts. Okay, they have asked the numericals regarding this. Okay, so now we are moving towards the actual switches. One by one, we'll discuss the actual switches. We'll start with the diode, next SCR, and after that we'll be moving towards the remaining switches. That is the thyristor family members, GTO, TRIAC, etc. Okay, so before that, let us discuss the majority charge carrier devices and the minority charge carrier devices, because in ESE or the GATE examination they have asked some theory bits, okay, related to which of the following is the majority charge carrier device, and they will give the options, okay, like a MOSFET, BJT, SCR, GTO, etc. Okay, so now let us discuss what is the majority charge carrier device and what is the minority charge carrier device. Okay, so majority charge carrier device. In the majority charge carrier device, the high breakdown voltage can be achieved by inserting lightly doped material on any one side of the PN junction. Majority charge carrier device means what? If the current is flowing or if the conduction of a device is due to majority charge carriers, okay, then it is known as the majority charge carrier device. And if the conduction is due to the minority charge carriers, then it is known as the minority charge carrier device. If you check the PN junction diode, in the PN junction diode, we are having the P-type layer, we are having the N-type layer, and in between that we are having the depletion type layer. We are having the depletion layer. Okay, and for the depletion layer, if you check across the at the depletion layer, at the P side, we are having the PN junction diode is like this. This is a P. This is a N, okay? And for the depletion layer, if you check at P side, we're having the layer of negative charges. And here we're having a layer of positive charges, right? And if the voltage is applied here, that is a plus here and a minus here, that is supply voltage, na? So it is like these negative charges will be getting attracted towards this, and these positive charges will be getting attracted towards this. So actually it is like a current is flowing through the, in the P-type material, can we say that the electrons are the minority charge carriers? And in the N-type material, the holes are the minority charge carriers. So that's why here the current is actually flowing due to the minority charge carriers. So that's why diode is a minority charge carrier device. Similarly, most of our devices are the minority charge carrier devices only. Okay, we're having very few devices those are the majority charge carrier devices. Okay, you can check in the MOSFET. Let us consider the N channel MOSFET. In the N channel MOSFET, there will be the formation of one channel, that is the N channel. There will be the formation of one channel, that is the N channel. Okay, and you can check the MOSFET circulation current, how the current circulates. In the N channel MOSFET, the current actually circulates due to the electrons. Okay, and that in your N type layers, the electrons are like a majority charge carriers. So that's why it is a majority charge carrier device. Okay, so now let us discuss. High breakdown voltage can be achieved by inserting lightly doped material on any one side of PN junction. Okay, means now we are going to discuss about the power devices, right? Power electronic devices. So in the power electronic devices and the signal level devices, what is the major difference? In the signal level, we are having the voltage rating and current rating is very less. But whereas in a power electronic devices, we are having the high voltage rating and the high current rating. Okay, so how to improve the voltage rating? Voltage rating means what? Voltage blocking capacity. Okay, voltage rating of a device is nothing but the voltage blocking capacity of that device. Okay, so now in order to increase the voltage blocking capacity of the device, yes, generally what we do, we insert a lightly doped layer into the device structure, and which layer we generally prefer, whether N minus or P minus, that we will discuss while discussing the diode. Okay, so same thing here. High breakdown voltage can be achieved by inserting lightly doped material on any one side of the PN junction. Second, in the minority, if you check here also, the high breakdown voltage can be achieved with lightly doped material. Okay, here also we are inserting the lightly doped material here. Here also we are inserting the lightly doped material. But the difference is, but in the minority charge carrier, what is happening? Due to the conductivity modulation, the on state resistance of the device is reducing. This is the major difference between majority charge carrier device and minority charge carrier device. What is the conductivity modulation? That you will understand while discussing. After this, we are going to discuss the diode. Okay, at that time you will understand what is the conductivity modulation. Okay, next. So due to the conductivity modulation, what is happening actually? The on state resistance of the device is reducing. It is reducing. Okay, but here you can check. Here we don't have the conductivity modulation process in the majority charge carriers. And due to that, the drawback of this is, yes, the lightly doped material will have high resistivity. Yes, lightly doped material is having a high resistivity, and this resistivity is high, and the conductivity modulation process is not there in the majority charge carrier devices. So due to that, the on state resistance of the majority charge carrier devices is high. On state resistance of the majority charge carrier devices is high. You can check. More conduction losses is there, na? Third bit. So more conduction losses is due to that high resistance, high on state resistance. Why the on state resistance of the majority charge carrier devices is high? Because the conductivity process is not there, right? Now, why the conductivity process is not there, that you will understand while discussing the majority charge carrier device, just like a MOSFET. Okay, and why what is the conductivity modulation process is there? Okay, what is that process and why it is present in the minority charge carrier device, that you will understand while discussing the minority charge carrier devices. Okay, so major difference here is, yes, you can check, due to the conductivity modulation process, the on state resistance is reducing, na? So as on state resistance is reducing, so therefore on state power loss as well as your on state voltage drop is also lesser compared to that of your majority charge carrier device. So till now, from first 2 points, okay, or let us add one more point, that is the less conduction loss. Okay, so if you check first 3 points, at one side we're having the majority charge carrier devices, at the second side we're having the minority charge carrier devices. In the majority charge carrier devices, yes, if the device turns on, its resistance will not reduces. But in the minority charge carrier devices, once the device turns on, its resistance reduces. Why? Due to the conductivity modulation. Now you can check, we are having both two devices, majority and the minority. In one case, the resistance is reducing once it turns on, and in the second case, the resistance is not reducing once it turns on. So if you check the conduction losses in both the case, suppose if through both the devices, if I am circulating the same current, then in which device the power loss will be more? Definitely the device in which the on state resistance is not reducing na, in that device the power loss will be more. So you can check, more conduction loss is there in the case of majority charge carrier device, whereas minority charge carrier device we are having the less conduction loss. Why the conduction loss is less? Because once device turns on, its resistance decreases, right? Its resistance decreases. Now, so if you check first 3 points, can we say that higher the device rating, higher will be the current carried by the device. So in which case the power loss will be more? My question is, suppose we are having the device with a higher rating. Okay, suppose I want to design a device, I want to manufacture a device, I want to construct a device, okay, for a higher rating. Let us consider the higher current rating. Okay, so which type of device generally we prefer, whether it will be a majority charge carrier or minority charge carrier? We need to prefer the minority charge carrier device only. Why? Because higher the rating means what? Higher the current carried by the device. If the device is carrying the higher current and if its resistance is not reducing at all after turning on, so what about the power loss in the device? Power loss in the device will be high na? We have discussed that the power loss is equal to, if device resistance is there, okay, then the power loss is equal to IRMS square into R1 na? If R1 is not reducing, so therefore power loss will be more in the majority charge carrier device. So that's why generally for high power applications, okay, majority charge carrier devices are not preferred due to their high conduction losses. Is this clear? But whereas we can prefer the minority charge carrier devices because they are having the less conduction losses. They are having the less conduction losses. Okay, so this is the about the first 3 points. Next, let us move towards the 4th point. 4th point, 5th point are very important. Okay, there will be no stored charge. Okay, the stored charge is not there in the majority charge carrier devices, but whereas there will be a stored charge in the minority charge carrier devices. The stored charge means what? Due to the conductivity modulation, when the charge carriers will be getting added into the lightly doped layer, okay, then it is like a resistivity of that lightly doped layer is reducing, okay. So due to that means what? In the n minus layer, that is in the lightly doped layer, external charge carriers are getting added. So it is like charges are stored by that layer. So this is present in the case of minority charge carrier devices. But whereas in the majority charge carrier devices, there is no such concept like a stored charge. Okay. And the drawback of the stored charge is that next point indicates the drawback of that stored charge. So you can check in the minority charge carrier device, we are having the stored charge present. How to find that stored charge? Generally, it is known as the reverse recovery charge. That you will understand while discussing the reverse recovery process in a diode. And also in the SCR also, right? We are having the reverse recovery process or the dynamic characteristic. In that case, you will understand. But please try to understand here key in the minority charge carrier devices, we are having the stored charge. Due to this stored charge, what is happening? The switching action will take more time. The switching action will be taking more time in the minority charge carrier devices. But whereas if you check, the switching action will take less time. Because here the stored charges are not present. Here the stored charges are present. How the stored charges relates to the switching action, that we will discuss. Because once the charges are stored, after that, while turning off that device, we need to remove those charges. And for removing those charges, it takes some time. And due to that, the switching action will take more time. Na? The meaning is this one. We require more time means why we require the more time in the minority charge carrier devices? Because here, first of all, we need to remove those stored charges. Here in the majority charge carrier devices, we don't have the stored charges. So there is no issue of removing the stored charges, right? Unless and until we remove the stored charges, our device will not be able to block the next voltage which will be applying, okay, for the next switching cycle. Okay, that you will understand within some time. Okay, so here let us check. Switching action will take more time, so low frequency and slow operation. Okay, so therefore, as the switching action is taking more time, so definitely the frequency will be the limitation will be having here, constraint will be having there. Okay, and the operation will be definitely slow, right? Here, so as the switching action takes less time, so high frequency and fast operation. So if you check the point number 4 and point number 5, from this we can understand that in the minority charge carrier devices, the switching action is taking more time. So it is having the limitation of the frequency or the switching frequency, right? But whereas in the majority charge carrier devices, right, switching action is taking less time. And here the frequency is a high. As the switching action is taking less time, so therefore we can use these devices for the high frequency. So where till now whatever we discussed, the first case was for the high power rating devices. Second one is for the switching action or the switching frequency. So if you check, minority charge carrier devices are generally preferred for high power rating due to as their on state resistance decreases once they turns on, and due to the reduction in the on state resistance, yes, what is happening, the conduction loss is also decreasing. So that's why for high power applications, definitely the minority charge carrier devices are preferred. Whereas if you check for high frequency applications, yes, for high frequency applications, can we use the minority charge carrier devices? No. Minority charge carrier devices are having the limitation, okay, of the switching frequency due to their switching action. Okay, it is taking more time. Okay, so that's why minority charge carriers will be having the lesser switching frequency compared to that of your majority charge carrier devices. So both these switches are having their superiority. One is having the superiority in the case of high power rating, and second one is having the superiority in the case of high frequency applications. Okay, so for high frequency applications, majority charge carriers are preferred. For high power rating, minority charge carriers are preferred. Okay, next. Now, important thing, the positive temperature coefficient, that is the PTC. Majority charge carrier devices are having the positive temperature coefficient, whereas minority charge carrier devices are having the negative temperature coefficient. What is the positive temperature coefficient and negative temperature coefficient, and how it affects on the device operation? Let us discuss. Negative temperature coefficient means what? As the temperature of the device increases, its resistance decreases. Yes or no? Positive temperature coefficient means as the temperature increases, its resistance increases. So suppose we are having a power electronic device which is carrying some current. Okay, when the current flows through the device, definitely some power loss will be taking place. Due to that power loss, yes, heat will be generated. Due to that heat, the device temperature will be increasing. Okay, and as the device temperature increases, what happens in the minority charge carrier device? Its resistance further reduces. But what happens in the majority charge carrier device? Its resistance further increases, na? So that is the drawback of majority charge carrier devices. Are you getting the point? It is having a positive temperature coefficient, but it is a slightly positive one. It is not very high PTC. It is a slightly positive variable. Okay. So this is the difference between the majority and minority charge carrier devices. Okay. But due to the negative temperature coefficient, generally the minority charge carriers are not advisable for parallel operation. Why? Let us discuss. Suppose I am connecting the two minority charge carrier devices. Let us consider we're having minority charge carrier devices, as you can check, SCR is there, diode is there, BJT is there, etc. Okay, so let me consider we're having a yes, SCR is here, and suppose the another SCR is connected here. Let us consider these two SCRs are connected in parallel. Initially, both the SCRs suppose are carrying the same current. Suppose this is I1, this is also carrying the same current I1. Now, suppose if the load is changed, if the load current suddenly changes, okay, because the how high the load changes and how the load changes, we don't know na. Our task is to fulfill the requirement of the consumer. Okay, so suppose after some time if the load changes, and due to that, suppose if this thyristor T1 and here it is thyristor T2, if thyristor T1's current increases first, suppose thyristor T1's current increases first, the meaning is here, let me write it as IT1. IT1 increases first. Actually, it is expected that whatever the current, right, whatever the current that is increased, that current should be equally divided na, in T1 and T2. This is the expectation. But our devices are having some characteristics. Due to that, which are those characteristics that you will understand while discussing the parallel operation of the SCR. Okay. So now here, due to the change in the load current, yes, thyristor T1's current, suppose it is increased first. If the thyristor T1's current is increased, if thyristor T1's current is increased, now what is the current that is flowing through thyristor T1? One is the I1 that was initially flowing, and second one is the IT1 is the additional current that is getting added into the thyristor T1. So now current in the thyristor T1 is greater than that of the thyristor T2's current. Now if the current in the thyristor T1 is increased, okay, so now can we say that here as the thyristor T1's current is increased, so that's why more power loss will be taking place in the thyristor T1. We know now power loss is proportional to your thyristor is like your modeled as a, we have discussed piecewise modeling. Thyristor is modeled as a resistor and a voltage source, resistor and a voltage drop, right? So if the current increases, definitely the power loss increases. So power loss of thyristor T1, that is, let me write PT1, it will increase. If PT1 increases, that is the power loss in thyristor T1 increases. Due to that, what will happen? Yes, therefore high heat will be generated, more heat will be generated in the thyristor T1. As more heat is generated in thyristor T1, what about the temperature of the thyristor T1? Temperature of thyristor T1 will be increasing. So thyristor T1 temperature will increase. And as the thyristor T1 temperature increases, and you can check, thyristor is a minority charge carrier device. It is having a negative temperature coefficient, yes or no, right? So as thyristor is having a negative temperature coefficient, and as the temperature increases, what will happen? Thyristor T1's resistance will further decrease, yes or no? So resistance of thyristor T1 will reduce. If the resistance of the thyristor T1 decrease, whether you can check the parallel branches, if one resistance is lesser, second resistance is more, through which branch the more current will flow? The branch whose resistance is lesser, through that branch more current will flow. So as here you can check, initially both the thyristors were carrying the same current. Due to the change in the load, thyristor T1 current was, yes, it has increased. Due to the increased current, thyristor T1 power loss increased. Due to the increased power loss, thyristor T1's temperature increased. Due to the increased temperature, thyristor T1's resistance decreased. Thyristor T1's resistance decreased means again more current will be flowing through thyristor T1 only. Is this clear? So this is the actual drawback. This is the drawback. Actually, the expectation is in ideal case, yes, this current should be getting equally divided. But what is happening? Once thyristor T1's current increased, again resistance is also decreasing. So that's why more current will be flowing through the thyristor T1 only. And at certain point, yes, our thyristor T1 may get damaged. So that's why here, yes, cooling system design is very, very important. Okay, as long as the power electronic switches are considered, cooling system design is very, very important. But appropriate cooling system, we can avoid this. Appropriate cooling system, we can avoid this. You will understand it, how to avoid this problem, okay, while discussing the parallel operation of the SCR. Okay, so generally it is not advisable to connect the devices, with the NTC in parallel, that is the minority charge carrier devices in parallel. But whereas you can check, if we connect the majority charge carrier devices in parallel, what will happen? If the current increases, then what will happen? The resistance, the power loss will definitely increase of that particular MOSFET. Let us consider the MOSFET. Okay, so as the resistance increases, so again the current flowing through that particular MOSFET, okay, will reduce now. And this is what expected. So for PTC we don't have problem, but for NTC we are having the problem. For NTC we are having the problem. Is this clear? Next. Now preferred for high switching frequency and low power applications. We have discussed, right? My majority charge carrier devices are preferred for, yes, high switching frequency and low power applications, right? Frequency is high. This is the advantage, okay? But it is also having the limitation of the low power, okay? We cannot use these switches for the high power applications due to their high resistance and the high power loss. Next, preferred for low switching frequency and high power applications, okay? Opposite. This is for low switching frequency because they are having the stored charges, and that's why the switching action is taking some time, okay? And high power applications it is preferred. Examples of majority charge carrier devices, MOSFET and Schottky diode. Whereas in the minority charge carrier devices, we are having the number of examples: power diode, SCR, GTO, power BJT, etc. Right? Now one device is missing here. That is your IGBT. Okay, IGBT is actually at the boundary of these two. IGBT is actually at the boundary of the majority and the minority charge carrier devices. IGBT is actually a minority charge carrier device only, because IGBT is a combination of your BJT and a MOSFET, and MOSFET is a majority charge carrier and BJT is a minority charge carrier device. And as I said, IGBT is a combination of these two, na, power BJT and a power MOSFET. Okay, so actually IGBT is a minority charge carrier device only, but it is having a positive temperature coefficient. It is having a positive temperature coefficient, means it is a minority charge carrier device, but it is having a positive temperature coefficient. Yes, positive temperature coefficient. So generally the IGBT is denoted at the boundary of majority and the minority charge carrier devices. Are you getting the point, right? It is at the boundary. Now, let us discuss the devices, their power capability and switching frequency. This table is important. Sometimes they ask the questions, theoretical questions, right? So as we discussed, the minority charge carrier devices are having the limitation of switching frequency, and they are having the superiority in the power handling. More power they can handle due to the lesser conduction losses. Okay, so you can check power semiconductor device, power capability and switching frequency. SCR is generally preferred for high power applications and low frequency. High power applications and low frequency. GTO is also minority charge carrier device. Okay, it is also preferred for high power applications and low switching frequency. SCR and IGBT both are almost same. Okay, GTO is having the advantage that by using the negative gate signal we can turn it off. Okay, next IGBT, which is at the boundary, na, right? IGBT is preferred for medium power and the medium power applications and the medium switching frequency applications. Power BJT, it is for medium power applications and the low switching frequency. Power MOSFET and TRIAC. Okay, TRIAC is generally you can check the wearing the power TRIAC as a fan regulator. We cannot compare the TRIAC with these above first 5 devices. Why? Because TRIAC is used for another applications. It is a bi-directional switch, na, right? So TRIAC is having the other applications. We cannot replace our SCR with a TRIAC. Okay, TRIAC is having its we can say the different domain, okay, of operations, right? So it is for the low power applications and low switching frequency, and MOSFET for low power applications but the high switching frequency. So whatever the devices we are having, in that the MOSFET is having the highest switching frequency. After MOSFET we are having the IGBT. Okay, after MOSFET we are having the IGBT. After that we are having the BJT. Next SCR, and next is the GTO. So here we are having the devices and their switching speed. MOSFET is the highest, IGBT, BJT, SCR and GTO, right? That switching speed, why for one device is high and second device is low? First of all, it is differentiated between the majority and minority. MOSFET is a majority, so that's why the frequency, switching frequency is a high due to the no stored charges. And apart from this, whatever the remaining minority charge carrier devices we are having, okay, in that it depends on their construction. Okay, so that we are having some difference in the switching frequency, right? So first one is without the diode, right? Only controlled switches, and second one is by considering the diode, right? So this is about the majority and the minority charge carrier devices. Next, now let us move towards the switching devices. So first of all, let us discuss the signal diode. Right? So we are not going to discuss here in detail the signal diode because it is a part of your analog electronics, right? So one more thing, one announcement is there. Yes. You are having the test on the analog subject on 26th August. Okay, 26th August from 4 to 4:45. 4 to 4:45, right? Next, so signal diode. Let us draw some concluding points from the signal diode so that we will discuss the power diode operation. Okay, so signal diode. What are the conclusions? When signal diode means what? It is your like conventional diode. When p-type material is at more potential, more positive than that of the n-type, it is like a diode is in a forward bias mode, right? So when diode is in a forward bias mode, the width of the depletion layer, whether it increases or decreases, come on, when diode is in a forward bias mode, the width of the depletion layer, whether it increases or decreases? Decreases, right? It decreases, right? So let me write, when PN junction is in forward bias mode, yes, width of depletion layer yes, it decreases, right? It decreases. Similarly, when PN junction is in reverse bias mode, when PN junction is in reverse bias mode, width of depletion layer increases, right? Width of depletion layer increases. Okay. So recall the VI characteristic of a signal diode. We are having, it is like this. Okay, voltage across diode, current flowing through the diode, right? Initially it is a leakage current will be flowing, right? And after that it will be having the shape like an exponential type of this. Okay, this type of shape. And next, similarly in the reverse bias, it will be like this. Okay. Correct. What this indicates, it is your reverse breakdown voltage. Okay. What this voltage corresponds? This voltage is on state voltage drop, na? On state voltage drop of a diode. In the case of silicon diode, it is a 0.7. In the germanium diode, it is a 0.3. Yes or no? In the germanium, it is a 0.3. In the silicon, it is a 0.7. Correct? Now, what this voltage indicates, 0.7 and 0.3. Suppose we are having a PN junction diode. Okay. As soon as when I connect the P type and N type materials together, there will be the formation of the depletion layer, right? So for the formation of depletion layer, the biasing is not required. Yes or no? Right? So as soon as P type and N types are connected together, there will be the formation of the depletion layer. Next, suppose we are having a silicon diode. We are having a silicon diode and some depletion layer is present in the diode. Some depletion layer is present in the diode. And if I apply the voltage of 0.2 volt, if I apply the voltage of 0.2 volt across that silicon diode, what will happen? Whether the diode will turn on? Whether the diode will turn on? Yes, I am applying the 0.2 volt across the silicon diode. The diode will not turn on. Why? Because why the diode is not turning on? Because the width of the depletion layer, okay, across the junction is still present there. If I purchase the diode from the market, okay, definitely there will be the depletion layer present. If I apply the 0.2 volt, the width of the depletion layer will decreases by some amount. If I increase the voltage from 0.2 to 0.3 volt, the width of the depletion layer will further decrease. If I increase the voltage from 0.3 to 0.4 volt, depletion layer width will further decrease. If I increase the voltage to 0.7 volt, the depletion layer width becomes 0. The meaning is when the supply voltage becomes equal to 0.7 volt, the width of the depletion layer across the diode or across the junction becomes equal to 0. And as soon as the width of the depletion layer becomes 0, it is like our diode is acting as a short circuit. Is this clear? So as we go on increasing the forward voltage across the diode, okay, diode terminals, that is from 0 volt to the 0.7 volt. In the case of signal diode, I'm saying, okay, from 0 volt to the 0.7 volt, the width of the depletion layer go on decreasing. Okay, at 0.7 volt, what is happening? The width becomes 0. Width becomes 0. So from 0 till 0.6 volt, from 0 till 0.6 volt, I'm saying, what was happening? Who was in opposition for the conduction of the diode? That depletion layer width was in the opposition for the conduction of the diode. Is this clear? the only thing that was opposing for the conduction of the diode is the depletion layer, right, which was present in the device. And how the depletion layer is formed? For for formation of the depletion layer, whether we need to connect the external supply across the PN junction? No. As soon as P type and N types are connected together, definitely there will be the formation of the depletion layer, right? So because P type are having the large number of positive charge carriers, N type are having the very small number of positive charge carriers. So that's why positive from P to the N will move here. From N to P, negative charges will move, and accordingly we'll be having the depletion layer. I will not go into that operation of the signal diode. Okay, the only thing is, important thing is, as the voltage increases, the width of the depletion layer decreases, and at 0.7 volt in the case of silicon diode, at 0.7 volt its width becomes 0. Once the width becomes 0, it is like our diode will be acting as a short circuit. Okay, diode will be acting as a short circuit, right? Next, and after that you can check here, the sudden increase in the current is there, right? The current is increasing suddenly. This is like an exponential rise here. This is like an exponential rise here. So from 0 volt to the 0.7 volt, what is happening? From 0 to 0.7 volt, yes, only very small current is flowing. That small current is nothing but your leakage current. That small current is nothing but the leakage current. Ideally speaking, that current should be 0. But in the practical case, yes, that current is some non-zero value will be there. It is in the range of microampere. Okay, it is in the range of microampere. Once at 0.7 volt, that depletion layer width becomes 0, the current increases suddenly. Current increases sharply. Are you getting the point, right? So now you can check here. If you check this, okay, if you check this one, this characteristic, where once after this point, we are saying that diode is in the conduction mode. So when diode is in the conduction mode, it will be having some voltage drop. And also whether this characteristic, you can check this characteristic, it is having some slope. Na? This characteristic is having some slope, right? So slope of this characteristic will give you, yes, it is a 1 by on state resistance of the diode. 1 by on state resistance of the diode. Because slope means what? It is a current, change in the current divided by change in the voltage. So it is a I by V. Na? I by V is like your 1 by resistance. So the slope of this characteristic will give you the 1 by R on. That is the on state resistance. So you can check, once diode turns on, definitely the voltage drop will be there 0.7 volt. But at the same time, current is also having some slope. And due to that slope of the current will be taken care by the on state resistance of the device. So that's why you can check the diode is represented in the piecewise modeling. We represented the diode with a resistor and yes, that on state voltage drop. That resistance is nothing but on state resistance, and that voltage drop is nothing but this voltage drop. It is we are saying. Okay, so piecewise modeling for the diode, you can check we are having the voltage source, right? That is the on state voltage drop, and in series with the resistor. Is this clear? Similarly, when diode is in the reverse bias mode, what will happen? The width of the depletion layer go on increasing. Ideally speaking, zero current should flow, but some leakage current will be flowing. That current is very, very small. Okay, depletion layer width is increasing. If we further go on increasing the voltage, depletion layer width will increases. Depletion layer width increases, and we are increasing the voltage across the device. So it is like a voltage is nothing but electromotive force. Okay, so as the force is increasing on that depletion layer at a particular voltage, yes, the breakdown of the depletion layer takes place, and suddenly very high current will be flowing through the device. Is this clear? This is what you might have discussed during your analog electronic course. Okay, now let us discuss the power diode. Let us move towards the power diode. So two concluding remarks we are taking. Yes, we can say that it is a dynamic resistance, right? Yeah. Silicon and the germanium, why breakdown voltage is different from, okay. It depends on their characteristic. Okay, silicon is having some more voltage drop, that is the on state required voltage, okay, to turn on the silicon diode, and germanium requires only 0.3 volt. Okay, it depends on their characteristic. Okay, next, now let us move towards the power diode. So we are taking the two conclusions from here. One is the when diode is in a forward bias mode, yes, what is happening? Width of the depletion layer decreases. Diode is in a reverse bias mode, the width of the depletion layer increases. Okay, now the difference between the power diode and the signal diode is that, yes, signal diode was for lesser voltage and lesser current, right? Now in the power diode, So as we are using it for high power applications, okay, so our main motto is to design the device, okay, so such that it should block the high voltage. It should block the high voltage. So how we are making, or we are we are making our diode capable of blocking the high voltage. So for that we are adding one lightly doped layer. You might be seeing that here we are having the p type, here it is a n plus. Actually generally this is a p plus, right? I have taken one case here, okay, and here whatever the density here, right, doping density, the same doping density is here, okay, but I have taken some case. It varies from application to applications and rating of the devices also. So you can check here, highly doped p type layer. P plus means highly doped. This is a n minus, that is a lightly doped n type material, and here we are having the n plus, that is the highly doped n type layer. So this is a heavily doped or highly doped. This is also heavily doped or highly doped, and this is a lightly doped. This is a lightly doped. Now the important thing we discussed during the first session only, the breakdown voltage. Okay, breakdown voltage is inversely proportional to doping density. Na? Just a minute. Yes, okay, so the breakdown voltage is inversely proportional to doping density. So breakdown voltage is inversely proportional to doping density. Doping density. Right? Doping density means what? Doping density means we are having the silicon crystal, right? That is a pure silicon crystal. That is a pure semiconductor. Into that we are adding the dopings, impurities, in order to get the p type and n type material. Okay. So if the layer is heavily doped, please don't raise the hands. I will answer all your queries at the end of the session. Okay. Yes. So breakdown voltage is inversely proportional to the doping density, and doping density means what? The doping density indicates the number of charge carriers present in that layer per unit volume. Number of charge carriers per unit volume, right? So doping density means number of charge carriers per unit volume. Okay, that is nothing but the doping density. So you can check here, if the doping density is more, the breakdown voltage will be lesser. Okay, and our task is, yes, to increase the breakdown voltage, that is the blocking voltage capacity. Breakdown voltage means the blocking voltage capacity of the diode. So that what we need to do, we need to, yes, reduce the doping density. So how to reduce the doping density? So here for that we have added a lightly doped layer into these two layers, p plus and n plus. Now lightly doped layer means we can add either p minus and n minus also. But why we have added only n minus layer? The reason is, if you add the p minus layer instead of the n minus layer, okay, then when the device is in a conduction mode, then the device conduction losses will increase. Why? Because the p minus layer will be having lesser conductivity compared to the n minus layer. The p minus layer is having the lesser conductivity compared to that of the n minus layer. Why the p minus layer is having a lesser conductivity compared to that of the n minus layer? Because in the p minus layer, the majority charge carriers are holes. In the n minus layer, the majority charge carriers are electrons. So if you compare the mobility of electrons and the mobility of the holes, in which case the mobility will be more? The electrons mobility is higher. You can Google it simply, okay, or you can check the material science books, okay. the electrons mobility is higher than that of the holes mobility. So what do you mean by the mobility? The mobility is nothing but how quickly your charges, are moving, okay, through that semiconductor material or through that metal when they are experiencing a electric field. Means when that semiconductor material or when the metal is placed in a electric field. Electric field means what? When it is connected to the supply. Okay, so when that metal or when that semiconductor material is connected to the supply, then how fast, how quickly your charges, right? Charges are moving. Okay, charges are moving towards the contact. That is nothing but the mobility. So mobility of electrons is almost 2 times that of the mobility of the holes. So now as the mobility of the electrons is faster or more than that of the mobility of the holes, so as we know, the rate of flow of charges is nothing but the current, right? So if the electrons are moving fastly compared to that of your holes, so definitely can we say that the current will be more in the case of electrons, that is the n minus layer, compared to that of the in the p minus layer, because p minus layer is having the lesser conductivity. The reason behind that is yes, the electron mobility will be more than that of the holes mobility. Is this clear? So let me highlight that point here. Yes. Voltage blocking capacity and that breakdown voltage both are having the same meaning, Vikrant. Okay. Okay. So yes, mobility of electrons, yes, is more than that of holes, So therefore conductivity of n minus layer, yes, will be more than that of conductivity of n minus layer will be more than that of p minus layer. So as the conductivity of n minus is more than that of the p minus layer, okay, so that's why during the conduction state, okay, during the forward conduction state, right, whatever the losses will be there, those losses will be lesser in the case of n minus layer. So that's why n minus layer is preferred. Okay, so therefore to reduce conduction losses, let me write to minimize the conduction losses, to minimize conduction losses, right, n minus layer is preferred. N minus layer is preferred over the p minus layer, right? So that's why generally we are using the n minus layer. Now we are having the heavily doped. Here it is a lightly doped and here it is a heavily doped. You can check the charge density here. It is a 1 into 10 to the power 18 per centimeter cube. Here n plus 3 into 10 to the power 19 per centimeter cube. This is one example I have taken. It is not like that the thumb rule is like here it should be the charge density is like this, here it should be like this, and here it is like this. No. Okay, one example I have taken, right? So in some of the cases you will observe that the charge density, okay, in the p plus and the charge density and the n plus, in both the cases it will be same. You can in some of the cases you can observe. Okay, so here you can check 10 to the power 18 per centimeter cube. Here it is 10 to the power 13 per centimeter cube. Okay, so there is a huge difference between the charge density. So that's why it is a lightly doped, this is a heavily doped, and this is a heavily doped. Okay, so in the construction we can indicate it like this, right? So, and also you can check the width of the, yes, this layer is generally known as the drift layer, right? This is a drift space now. So this layer is known as a drift layer. Let me indicate, this is a drift layer, right? So now the width of the drift layer, it indicates how is the breakdown, what will be the breakdown voltage for this particular device. If I want the more breakdown voltage or more blocking voltage, breakdown voltage, blocking voltage, both are same. Okay, so if I want the device to block more voltage, right, the width should be increased, right? So now, yes, the width of the depletion drift layer indicates the breakdown voltage of the device. Okay, so let me write the width of drift layer. More the width of drift layer, more will be the blocking voltage or the breakdown voltage. Breakdown voltage, or let me write it as a blocking voltage. Right? So next, so this device we have indicated like this. Now let us check how it operates. So let me redraw this device as, at one side we're having the P plus. You can check the widths of the P plus and N plus. It is a very small compared to the, right, N minus, and here it is a N minus layer. That is the drift layer. This is the anode. This is a cathode. Okay, only two terminal device. Symbol of the diode we know. Okay, next. So how many junctions will be here? 1, 2, 3, 4. Some are saying 2, 1, 2, 1, 2. No, only one junction is there. The junction is formed between P and N type material. Here you can check, this is N minus, this is N plus. It will not form the junction. Okay, P plus and N minus, it forms the junction. P plus and N minus, it forms the junction. So here we are having the junction. Here it is a junction. Okay, so only one junction we are having. Definitely across this junction we will be having the depletion layer present, right? For the depletion layer at this side we are having the, at P plus side we are having the layer of negative charges. At N minus side we are having the layer of positive charges. Okay, so when the forward voltage is applied, what will happen? P plus will be at the more potential than that of the N minus. Okay, so it is like our junction, this P plus N minus junction will be in the forward bias mode. So width of the depletion layer go on decreasing. Okay, width of the depletion layer go on reducing. Okay, and after some voltage, generally the voltage drop for this diode, power diode, okay, it is in the range of around 0.7 volt to 1.5 volt. 0.7 volt to 1.5 volt. Okay, so when the forward voltage is applied, the width of the depletion layer decreases, right? Width of the depletion layer decreases. So it is like we're having the negative charges here, and at this side the layer of positive charges. Right? So when forward voltage is applied, it is like, yes, depletion layer width decreases. Same conclusion I am taking from the signal diode. Okay, depletion layer width decreases. Okay, as the width is decreases, so it is like we don't have a problem now, because the depletion layer is the only reason which opposes the turning on of a device now, right? So if I apply the sufficient voltage, definitely this width becomes zero. And after that particular voltage, our device will turn on. So when diode is in a forward bias mode, we don't have the problem. Definitely after some voltage, our device will turn on. Let us check what will happen to the reverse bias. Before that, let us discuss the conductivity modulation. what is the conductivity modulation? Suppose if I increase the voltage, between anode and cathode, okay, so that the width of the depletion layer is decreasing, and at a particular voltage, right? Suppose it is a 1 volt. At that 1 volt, the width of the depletion layer becomes 0, and our device is acting as a short circuit. Suppose our device is acting as a short circuit. Yes, just a minute. So here, yes, this is a P plus N minus. Now suppose this is acting as a short circuit. So when device is acting as a short circuit, means width of the depletion layer becomes 0, right? So this P plus layer and this N plus layer, this P plus layer and the N plus layer, this will inject charges. Into this, yes, N minus layer. Initially, if you check here, we are having the density, charge density of this N minus layer is very less. Once device starts conduction, it is like at this side we're having the heavily doped p-type layer, heavily doped N plus layer. And once this layer becomes short circuit, okay, once device becomes short circuit, this P plus layer will inject the charges into the N minus layer. And this N plus layer also will inject the charges, negative charges into this N minus layer. Due to that, what will happen? Initially, the lesser number of charges were there in the N minus layer. But now from both these sides, P plus and N plus, from P plus and N plus side, yes, we're having the large number of charges. Those will be getting added. Okay, those will be getting added into this N minus layer. So what about the conductivity of that N minus layer? It will be further enhanced. The conductivity of N minus layer will increase. Are you getting the point? The meaning is the resistivity decreases. The resistivity of that N minus layer decreases, because in any layer, if the charges are present, more number of charges are present, so it is like the resistivity of that layer reduces, conductivity increases. Initially, N minus layer had the more conductivity than that of P minus layer. So that's why instead of P minus, we preferred N minus layer. Definitely N minus layer is having a more conductivity than that of the P minus layer. But now, if you connect like this, P plus, N minus and N plus, okay, in the device construction, if you compare P plus and N plus conductivity and the N minus layer conductivity, which layer will be having the lesser conductivity? N minus layer will be having the lesser conductivity, because it is having a lesser charges, Now, once the device turns on, this P plus will add the positive charges. This N plus will add the negative charges into this N minus layer, So due to that, what will happen? The conductivity of that N minus layer, yes, increases. Conductivity of N minus layer increases. Now you can check, conductivity increases means resistivity decreases. Conductivity increases means resistivity decreases, and that is nothing but the conductivity modulation. We are changing the conductivity, na? Modulation means what? Conductivity changing. Okay. So conductivity modulation means what? Conductivity changing. How it is changing? When device turns on, the P plus layer will inject the positive charges. N plus layer will inject the negative charges into this N minus layer. Okay. And due to that, the conductivity of the device increases, resistivity decreases. Right? So like this, what will happen? As the device go on in the conduction mode, okay, large number of charges will be getting added from P plus to this N minus and N plus to this N minus. Okay, so that's why number of charges will be getting added into this N minus layer will be getting increased, and that is nothing but your stored charge. In the minority charge carrier devices, we have discussed one concept, that is the stored charge. The stored charge is due to the conductivity modulation. What is the conductivity modulation? Conductivity modulation is nothing but from P plus, the charges are getting added here, positive charges. From N plus layer, the charges will be getting added. These are the negative charges. Because both sides were having very less area or very less volume of this P plus and N plus. And after that, we are getting the charges are getting added. Now, definitely this P plus will be coming out from this. These positive charges will be coming out from P plus to the N minus once device starts conduction. Okay, so this will happen when device will be in the conduction mode. Now, when device is in a reverse bias mode, then what will happen? Right? So suppose I have placed the reverse voltage. I have maintained the reverse voltage across the device. So what will happen? Right? What will happen? difference between n minus and n plus is, these are the basic things. N minus is a lightly doped. Layer means n type material. N plus is a heavily doped, right? Heavily doped layer. Again, it is a n type layer only. N type material. Means in a silicon crystal, right? Yes, if we add the impurities such that the large number of electrons will be getting added, okay, then it will be like a n plus. You can check from here, you will understand. The density, na, 1 into 10 to the power 18 per centimeter cube. Okay, that is per cm per unit of volume, right? We are having 1 into 10 to the power 18 positive charges in this P plus, whereas in this we are having n plus 3 into 10 to the power 19. Okay, 3 into 10 to the power 19. Okay, this number of negative charges we are having per unit volume, okay, and here it is a 3.1 into 10 to the power 13. The power you can check here, it is only 10 to the power 13. Here it is 10 to the power 18. Here it is 10 to the power 19. So in which layers the large number of charges will be there? In P plus and n plus, na? In the n minus, we are having the lesser number of charges, okay, and definitely P plus large number of positive charges, n plus large number of negative charges, and n minus lesser number of negative charges. Okay, next, these are the majority charges actually. Next, let us discuss when diode is in a reverse bias mode. When diode is in reverse bias mode, so suppose same we are having P plus n plus, P plus, here it is a n minus, and here it is a n plus we are having. So the reverse voltage is maintained, and let us consider here it is a load. R minus plus, suppose this is a Vs. Okay, next, suppose this reverse voltage is a variable voltage. Reverse voltage is a variable voltage. Now next, P plus n minus will be having only one junction. This will not form the junction n minus n plus. This will not form the junction because here also we are having the n type layer. Here also we are having the n type layer. So it will not form the junction, right? The junction is only one. That is a junction is always formed between P and n type material only. Okay, so we are having only one junction. Now suppose, yes, between P plus and n minus, we are having the layer of negative depletion layer will be present. So here it is negative charges, and at the n minus side we will be having the layer of positive charges. Next, when the reverse voltage is increased, what will happen? The width of the depletion layer will increase. The width of the depletion layer will increase. But if you check here, when the depletion layer is present here, the n minus layer is having, we know now it is a lightly doped. So that's why the resistivity of this n minus layer is more. Resistivity of this n minus layer is more. Okay. So when the negative charges here from the negative plate of the battery will try to enter here, the positive charges from here will try to enter into the device structure like this, just like your signal diode. So due to that, what will happen? The width of the depletion layer will go on increasing. Means from this, okay, positive charges which are coming from the positive plate of the battery will be entering into the n plus, will be recombining with the negative charge carriers into the n plus, right? And after that, whatever the additional charge carriers are coming, okay, these will be again passing towards this n minus layer. Now you can check here, as the width of this depletion layer, n minus layer is a very high. Width of the depletion layer, that is width of the n minus layer, not the depletion layer. Width of the n minus layer is very high, na? Right? So we are having a very large scope, means the depletion layer is having a very large scope, right? To increase its width, to grow, to increase its width, that is the to grow. So due to this, what will happen? If I go on increasing the voltage, if I go on increasing the voltage, the width of the depletion layer will go on increasing only, will go on increasing only. But if you check in the signal diode, in the signal diode, we're having the limitation now. We're having the P type layer and N type layer. But what is the width of those layers? The width is very less. But here in the power diode, as this width is more, yes. So here we can, yes, the as the width is more, our what I can say, yes, our depletion layer will be having more scope to grow, right? More scope to grow. So that's why if we go on increasing the voltage, its width is go on increasing. So at a certain voltage, what will happen? The breakdown of this depletion layer takes place. Why it is taking place, the breakdown? Because what we are doing, you can check here. This is a minus, this is a plus, and this is like your EMF, na? This is like your EMF, electromotive force. Means indirectly what we are doing, we are, yes, we are increasing the force on the device. We are increasing the force on the device. As the force on the device increases, the width of the depletion layer increases. At a certain voltage, at a certain value of the force, right? At a certain value of the force, right? The device, the depletion layer will break down. Depletion layer will break down. Okay, and that generally we know it as a reverse breakdown of the device. Reverse breakdown of the device. Is this clear? So ultimately, here we are having the large scope for the depletion layer to grow, and as the scope is more here to grow, that is the more space is available for the depletion layer to grow. So that's why the required voltage to break down that depletion layer is also high. If you compare the signal diode, this N minus layer is not present now. So that's why these P plus and N plus layers will be, yes, in the signal level device, it will be like this now, P plus, and here it is a N plus. So how much, whether the depletion layer is having large scope here to grow in the signal level device? No. But whereas in the power level devices, we are having, in the power diode, we are having the large scope. Okay, so that's why here we have added this N minus layer, and the width of the N minus layer is also high. So more the width of the N minus layer, more will be scope for the depletion layer to grow, okay, to increase. Okay, and that's why the more voltage will be required to break down that depletion layer. Is this clear? Right? So this is the diode operation when it is in a reverse bias mode, right? And similarly, forward bias, it is similar to that of your signal diode only. The only thing is the conductivity modulation will be taking place there. Now let us discuss the VI characteristic. Let us discuss the VI characteristic. After that, we will take the we will go for the break. Okay. VI characteristic, it is similar to that of your signal diode. The only thing is the slope. This is a voltage, this is a current. Okay, V means voltage across the device, I means the current flowing through the device. Okay, in the signal diode, we discussed we are having the exponential type of the curve, but here we are having the linear type of curve. Okay, so curve is like this. Very small leakage current will be flowing. Okay, this is the voltage drop, on state voltage drop of the device, and after that we'll be having a linear type of curve. We'll be having a linear type of curve. This type of curve we'll be getting. This is a linear in power diode. Linear in power diode. But whereas in signal diode, it is exponential. In a signal diode, it is exponential. Again, means what is happening after this point? You can check after this point. Yes, what is happening? The device is turning on. Turning on means width of the depletion layer becomes 0. This is a forward bias. I am saying this is a forward bias, na? Forward bias. And what this indicates? It is a on state voltage drop. On state voltage drop of device. On state voltage drop of device. Right? Next. Similarly, in the reverse bias, it is similar to that of your signal diode only, but the thing is the required reverse voltage, the required reverse voltage for the breakdown of the depletion layer. Yes, here the value is more. Okay, value is more, right? Very small leakage current. After that, it is a very high current will be flowing. Now, this voltage is your VBR. That is a reverse breakdown voltage. Okay, reverse breakdown voltage. This is the on state voltage drop. This is the reverse breakdown voltage. Now you can check once the reverse breakdown voltage is reached. Once the reverse breakdown voltage is reached, means once the VBR is reached, what will happen? Once the VBR is reached, suddenly very high current is flowing. So why very high current is flowing? Because the breakdown of the depletion layer is taking place now, and we are having the large number of charges. Those charges will be freely moving, and rate of flow of charges is nothing but the current. Okay, so due to that, what will happen? Yes, the sudden current will increase. Sudden current will increase sharply. But let me know, this curve is only for theoretical purpose. This curve is only for theoretical purpose. If you want to operate the diode, if you want to operate the diode at the operating point, suppose at this operating point I want to operate the diode, in a practical case our diode will get permanently damaged. Why? Because if you check, corresponding to this operating point, the voltage across the diode is very high. Current flowing through the diode is also very high. This is the current flowing through the diode. This is a high current, and the voltage across the diode is this voltage. This is also very high. So high voltage across the diode and high current flowing through the diode. So high power loss will be taking place. Due to the high power loss, high heat will be generated, and due to that high heat, yes, our device will get damaged permanently. So always keep it in mind. This vertical line is only for theoretical understanding. Okay, but if we want to operate the device at this operating point, okay, that is a high current and high voltage, our device will get damaged. So the questions in one of the examinations, they asked the question, we can circulate the current, or our diode can carry the rated current in forward direction. Diode can carry the rated current in forward direction, but when the same rated current is circulated through the diode in the reverse direction, then the diode will get damaged. The reason is because corresponding to the rated current in the forward direction, you can check the voltage across diode is very small now. Suppose this is a I rated. Okay, if I circulate the rated current in the forward direction, the voltage across device is very small, so therefore the power loss will be very small. So that's why heat generation will be lesser. Okay, and our device, yes, will not get damaged. But if I want to circulate this same rated current in the negative direction, okay, that is the negative I rated, then the device is getting damaged, because corresponding to this negative, that is minus I rated, the voltage across device, because corresponding to this point, the operating point is only on this vertical line. Okay, so therefore the high voltage across the device is this voltage, is nothing but this voltage, na, right? So high voltage and the high current, so device will get damaged due to the high heat generation. Is this clear? Right? So because here on state, here the voltage is very less, here the voltage is high, corresponding to the same rated current. Okay, so that's why we cannot circulate the rated current through the diode, okay, in a reverse direction. Otherwise it will get damaged. Is this clear? So this is the simple power diode, similar to that of your sir, why it is a linear in forward bias? Because you can check the signal diode, we are having the exponential, because at both the sides p plus and n plus layers we are having, and there the large number of charge carriers are present, so that's why current will increase very sharply. But whereas in power diode, we are having the n minus layer, lightly doped layer is there, so that's why the curve is linear. Right? Sir, break up to 7:30. Okay, so a simple operation similar to that of your signal diode. The only thing is, please try to understand, the only thing is we are adding the n minus layer. Why the n minus layer is preferred over the p minus layer? That is the important thing. Okay, what is the conductivity modulation, and how the conductivity modulation, due to the conductivity modulation, how the resistivity of that layer decreases, and due to the as the resistivity decreases, therefore the on state resistance also decreases now. So therefore you can check in minority charge carrier devices, and once device turns on, its conductivity, due to the conductivity modulation, its resistance, on state resistance decreases. Right? Same thing. We'll take a break here. Yes, Ramakrishna, do you want to say something?
Yes, sir. In the numerical 2, you have written wrong answer.
Which numerical?
Numerical 2.
Yes, here.
Oh, it is 2, 4, sir. You have explained 2, 4 and you have tick marked 1 and 4 there.
Okay, like that. Huh? Just
Yes, sir.
let me check. Okay. I explained it 2, 4.
Yes, sir. Yes, and correct is 2, 4.
I'm sorry. Yes, please
Yes.
correct it. Thank you.
Yeah. And can you keep the homework question slide and go for breaks?
Yes.
We
Definitely.
will note it down. So that's
Okay.
you are
It
removed
is a
fast.
2 and 4, no?
Yes, sir. 2 and 4 it is.
Just a minute. Okay, we'll take a break here. We'll start at 7:30, right? Okay. 2 and 4. Right? This is a homework question. Okay. So now we are going to discuss the reverse recovery process in power diode. Okay. So, reverse recovery process is nothing but when the device is in a conduction mode. At that time, due to the conductivity modulation, when the charges will be getting added into the n minus layer, right? So those charges we need to remove. And that process is nothing but your reverse recovery process, right? So let us discuss. Suppose, yeah. Here the current flowing through the device, voltage across the device. Okay. Suppose initially the device is in a on state. So very high current is flowing through the device, right? So device is in a conduction mode. So high current is flowing into the device. So therefore voltage across the device is also very low. That is the on state voltage drop. Correct? So this is the on state voltage drop. And this is a current I. Okay. Device is in a conduction mode. Now, when the reverse voltage is applied across the device, so what will happen? If you check, when we purchase the diode from the market, okay, at that time there will be the depletion layer already present. When the device is in a conduction mode, whether the depletion layer will be present there? No. So as the depletion layer is not present, so that's why if I maintain the reverse voltage, our device will take some time to block that reverse voltage. Okay. And during that time, what is happening, that we are going to discuss now. Okay. So when the reverse voltage is applied across the device, so first of all, the current flowing through the device, it goes on increasing, it go into the negative direction. Why it is go into the negative direction, we will discuss. This is the reverse voltage which we have applied. Okay, VR. This is the reverse voltage. Now, so let us discuss here. So we are discussing, suppose the device is in an on state, and now we are interested in turning it off. Okay, so we have applied the reverse voltage across the device. So when the reverse voltage is applied across the device, we expect that as soon as the reverse voltage is maintained across the device current should suddenly decrease to the zero value. Suppose we are having a power diode which is in a conduction mode. So depletion layer is not present because diode is acting as a short circuit. Depletion layer is not present, right? So when the depletion layer is not present and if the reverse voltage is applied, so we expect that yes, the current flowing through the device will suddenly reach to the zero value, but it is not happening into the device. Why this is not happening? Why? The reason is when the device is in a conduction mode, due to the conductivity modulation, yes, there will be the charges from P plus and N plus layers. Those will be getting added into the N minus layer, right? So first of all, in order to successful turn off the device, yes, those charges should be getting removed. Those charges should be getting removed. Okay. So due to those charges, when as soon as at this point, actually here at this instant, we have initiated the turn off. Here we have initiated the turn off. At this instant, we have initiated the turn off of a diode. Initiated turn off. Okay, of diode. But if you check, if we initiate the turn off process at this instant, it is expected that at this instant only the diode should show the reverse voltage, but it is not happening. You can check, actually the diode is, yes, diode is blocking the reverse voltage only after this instant, So you can check from at this instant, I have maintained the reverse voltage. So here I have applied the reverse voltage, but the reverse voltage is appearing across the diode after this much of time, So let me write here, reverse voltage is applied across the diode. Reverse voltage applied across diode, right? Now, why the diode is taking this much time, right? So from here till here, why the diode is taking this much time, right, to turn off or to block that reverse voltage? Okay, the reason is, first of all, let us check. Suppose if we purchase the diode from the market, definitely in that structure, the depletion layer will be present. And if we maintain the reverse voltage, now if the depletion layer is present, suppose, and if I am applying the reverse voltage, so whether our diode will immediately block that reverse voltage? Yes. Why the diode has blocked the reverse voltage immediately? Because the depletion layer was present there. But now here, when the device is in a conduction mode, at that time the depletion layer is not present. And during the conduction mode, what is happening? The point is, when the diode is in a conduction mode, due to the conductivity modulation, when diode is in conduction mode, due to conductivity modulation, yes, due to conductivity modulation, yes, charges will be getting added. Into n minus layer, right? So therefore, if I want, right, my diode to be able to block that reverse voltage, so first of all, we need to remove those charges. Okay, and second thing, once the charges getting removed, after that the depletion layer will be formed, and after that our diode will block that voltage. Now let us check what is happening inside the diode. Actually, what is happening? As I said, from this point till this point, diode is in a on state only, right? From this point to this point, diode is in a on state. That is a conduction mode. Depletion layer width is 0. Charges will be getting added into the n minus layer. Okay, now this is a purely theoretical bit, so please be focused. Okay, so now charges will be getting added into the n minus layer, so conductivity of the n minus layer is increased, right? So now at this instant we have initiated the turn off. How we have initiated the turn off? By maintaining the reverse voltage. By maintaining means here we have applied the, corresponding to this point, we have applied the reverse voltage across the diode. Okay, now as soon as the reverse voltage is applied, the current flowing through the diode will not become 0 suddenly. The current will go on decreasing. Okay, the current will become 0. And after that it goes into the negative values. Why the current is going into the negative values? The reason is due to the added charge carriers into that n minus layer. Okay, so suppose in the n minus layer, we are having, let us consider in the n minus layer, yes, this is the structure of diode. here it is a P plus, here it is a N plus, and here it is a N minus. When device is in a conduction mode, due to the conductivity modulation, yes, here the large number of charge carriers will be getting added. That is a positive as well as negative, right? Positive as well as negative. Large number of charge carriers. Let us consider 1000 positive charge carriers and 1000 negative charge carriers are getting added into the N minus layer, right? The charge carriers were not present, not available when we purchased the diode from the market. But due to the conduction, okay, when the device is in the on state, at that time the charge carriers will be getting added. The charge carriers will be getting added. Okay. Now, as soon as the reverse voltage is maintained, right? The charge carriers, right? The charge carriers which are present into the N minus layer, okay, the charge carriers will be getting neutralized by the recombination. Will be getting neutralized by the recombination. Okay, so here you can check 1000 charge carriers are present. For example, I have considered one number. Okay, so now you can check when the reverse voltage is maintained, the charge carriers will be getting neutralized. Suppose 1000 charge carriers are present. At a time, all the charge carriers will be getting attracted, right, towards positive, will be getting attracted towards negative, negative will be getting attracted towards positive. And as we know, the current is nothing but the rate of flow of charges. Okay, so that's why current will be increasing. Current will be increasing. So here we'll be having the current which is going into the negative value. Once almost 60% of the charge carriers, almost 60% of the charge carriers, right, out of these 2000, once almost 60% of the charge carriers, that is the remaining charge carrier will be 60% of these 2000. Okay, will be remaining, will be almost 60% of the charge carriers will be getting neutralized. After that, the current is decreasing. Current is decreasing because you can check. Suppose 60% of charge carriers are getting neutralized. Means what? From here the 600 are getting neutralized. From here the 600 are getting neutralized. So suppose only we are having remaining 400 here. Here it is a 400. So what is the rate of flow of charges now? The rate of flow of charges will be definitely lesser than that of when the 1000 and 1000 present, right? So due to that, when only 40% charge carriers are remained, then the current go on decreasing. Here the current go on decreasing. Okay, so that's why here we are having the negative peak, and after that the current is decreasing. This negative peak and the current decreasing, this is only due to added charge carriers into the N minus layer, right, during on state of the diode, due to the conductivity modulation. Now you can check here from this point. Actually we have initiated the turn off of a diode at this point. So we have maintained the reverse voltage, but actually the voltage across the diode, yes, is negative. Actually the voltage across the diode is negative only after this point. Means once 60%, almost 60% of the charge carriers which were added into the N minus layer, okay, after the neutralization of those charge carriers, after the neutralization of those 60% charge carriers, yes, it is like our diode is now trying to block that voltage. But from this point to this point, the diode is still in the conduction mode only. And after that, you can check here the current is decreasing and diode current voltage is increasing. Okay. Now after this, once 60% charge carriers are getting neutralized, means only 40% are hardly charge carriers are remain. Okay, so that's why current is decreasing. Okay, so here voltage is maintained like this. This is a negative voltage. This voltage or this negative voltage peak, let me write it as VRM. This is due to the stray inductance. Of the device. This is a VRM. The VRM is due to stray inductance of device, right? Next you can check once current decreases, and if the current reaches almost, let me indicate here, this is your negative peak current. Let me write it as a IRM. This is a IRM. When the current becomes equal to 25% of IRM, 25% of reverse peak current, reverse maximum current. IRM means what? Reverse current, and it is a maximum, right? Reverse maximum current. When the current reaches equal to 25% of IRM, we can say that Now our diode is successfully blocking the reverse voltage. Now our diode is successfully blocking the reverse voltage. Now, so here we are having this curve. We are having this curve. In this, we are having 2 times. Let me indicate. Yes. One is a TA, second one is a TB. This time from here to here, this is a TA, and the second time is this one. From here to here, it is a TB. TA here and TB here. And the total time is TRR. That is the reverse recovery time. Reverse recovery time. Right? This is a TRR. TRR. Okay, so let me write TRR is a reverse recovery time. TRR is a reverse recovery time. Okay, TA is the time corresponding to the neutralization of almost 60% of added charge carriers into the n minus layer, and TB is the time corresponding to the neutralization of remaining 40%, okay, of the charge carriers getting neutralized. Okay, so the current reaches into the negative value, and again it reaches to the decreases, that is reaching towards the 0 value. And here we are having the voltage. Now you can check, after this point only our diode is blocking the voltage. After this point only we can say that our diode is ready to block the voltage. Ready to block the voltage. Okay, so it is not like that. If I maintain the reverse voltage and immediately our diode will turn, immediately our diode will block that reverse voltage. No, it will take some time. It will take some time, and depending on this TRR, okay, we are having the types of the diodes. Okay, and from that we decide generally which diode is used for which application. Right? If we want the inverter, then we require a faster diode. If we use in the case of rectifier, somewhat slow speed diode is also can do the job. Okay, like this. Now, so here, yes, related to this we are having one term, that is the softness factor, or it is also known as a snappiness factor. They have asked the numericals related to this characteristic. Okay, we'll discuss how to simplify it. Right? So related to this TRR and TATB, we are having one term, that is the softness factor. Softness factor, or it is also known as a snappiness factor. It is denoted with letter S, which is equal to TB upon TA, which is equal to TB upon TA. Okay, so if TB is very less than that of the TA, then the diode is known as the fast recovery diode. Okay, if TB is very less than that of the TA, okay, means TB is very less than that of the TA, then the diode is known as the fast recovery diode. Then it is a fast recovery diode. Fast recovery diode. So you can check here. TRR means what? TRR is equal to TA plus TB. Na? Reverse recovery time is this one. This is the reverse recovery time we are having total, which is equal to TA plus TB. Okay, so in the case of fast recovery diode, TRR is equal to only TA, nearly equal to TA. Okay, nearly equal to TA. Means what? If the TB is very small, suppose this TB is very small, then we can say that this TRR will be very less. Na? TRR will be very less. It is nearly equal to TA only. So that's why reverse recovery time is lesser. The meaning is, yes, diode is having a fast recovery. That's why it is a fast recovery diode. That's why it is a fast recovery diode. Are you getting the point, right? Now, related to this term, we are having as long as the diode is considered, we are having the two important terms. One is the reverse recovery charge, and second one is the reverse recovery time. Okay, reverse recovery charge and the reverse recovery time. So here, let us consider this change in the current. Okay, change in the current with respect to time. Let us write it as a DIA by dt. Let me write this as a DIA by dt. I'm writing here di by dt. Instead of DIA by dt, let us write it as di by dt, because we have considered here I. This is a di by dt. Di by dt means rate of change of current with respect to time, right? Rate of change of current with respect to time. Now, suppose if we approximate this curve, as a triangle, okay, means I am approximating this term as a triangle. So it will be like this. Yes. So here, this is a, yes, increasing, and it will be like this. Suppose I am approximating this curve as a triangle. So can we say that area under this curve, that is the area under the triangle, is nothing but what? Yes, it is like your reverse recovery charge. Area under this triangle is nothing but your reverse recovery charge. Okay, let me write area of triangle is equal to what? QRR. QRR means reverse recovery charge. Let me write QRR is the reverse recovery charge. It is a reverse recovery charge. Reverse recovery charge, which is equal to what? It is the area under the triangle. Area under triangle. Okay. Now, what is the area under triangle? We know it is, therefore we can write QRR. QRR is equal to, can we write area under this triangle is equal to what? QRR into this height, it is a IRM, into TA plus TB matlab means TRR. Okay, so we can write it is a 1/2 into IRM into TRR. Okay, 1/2 into IRM into what? It is a TRR, right? 1/2 into IRM into TRR, right? Consider it as equation number 1. 1/2 into IRM into TRR. That is the reverse recovery time. Okay, reverse recovery charge. Okay, means whatever the charges those were getting added due to the conductivity modulation when device is in the conduction mode, right? Those charges are nothing but your QRR, and those charges we are now removing, we are recovering, na? So that's why it is a QRR, reverse recovery charge, right? Next, now can we write the expression for IRM in terms of di by dt? You can check. IRM is this current, IRM is this current, and this rate of change of current with respect to time is di by dt. So can I write corresponding to TA during TA di by dt is equal to change in the current, na? What is the change in the current? Di means change in the current. What is the change in the current? It is changing from 0 to the IRM. So change in the current is IRM minus 0. So that is the IRM. Okay. So change in the current is IRM, that is di is equal to IRM. And what is the change in time? Change in time is TA. Okay. So let me write during TA. Yes, di by dt is equal to IRM divided by TA, right? So therefore we can write IRM. Therefore IRM is equal to what? It is a TA into di by dt. TA into di by dt, right? So next, so this is QRR and this is IRM. Now we are going to write the expression for TRR and QRR. Okay, TRR and QRR. Those expressions are very, very important for fast recovery diode, actually, right? For fast recovery diode. So let me write for fast recovery diode. For fast recovery diode, for fast recovery diode, what we have written? TB is very, very less than TA, na? TB is very, very less than TA. TB is very, very less than TA. So therefore TRR is equal to TA only, right? TRR is equal to TA only, right? So now here in IRM equation, suppose in this IRM equation, can I replace this TA with this TRR? Can I put this TA, which is equal to TRR, in this equation? Yes. So therefore I can write, therefore IRM is equal to what? It is a TRR into di by dt. TRR into di by dt. Okay. Now this is IRM is equal to TRR into di by dt. Can I yes, can I replace, can I put this IRM? Can I put this IRM here? Can I put this, that IRM in this equation 1? Yes. So therefore put this IRM in equation 1. In equation 1. So you can write equation 1 is QRR is equal to, so therefore QRR is equal to 1/2 into IRM, na? But instead of IRM, put this term. So it is a TRR into di by dt. Okay, this is actually IRM into we are having TRR into TRR, right? So into TRR. So it is like QRR. Let me write the small QRR because we have used the notation small, right? So therefore, QRR is equal to 1/2 into TRR square into di by dt. Okay. So from this, can we write TRR? Therefore, TRR is equal to under root 2 into QRR, right? Divided by di by dt. This is the equation for reverse recovery time. For fast recovery diode, because we have considered here for fast recovery diode, right? For fast recovery diode. Next, if this is the expression for TRR, now can we write the expression for QRR? Yes, we are having the QRR. You can check here. We are having the QRR is equal to 1/2 into IRM into TRR. Okay. Now let me put here. Yes. In the QRR expression, right? So let me write therefore QRR, right? QRR in this equation, let me put, okay, IRM is equal to TRR into di by dt, na? TRR into di by dt, right? So replace here, okay, replace here TRR with this expression, right? Also, so therefore let me write IRM is equal to TRR means this term under root 2QRR divided by di by dt into di by dt. So one di by dt and this under root di by dt will get cancelled out. So therefore IRM is equal to under root 2QRR into, it will be like a di by dt. This is the expression for IRM. From this expression, we can write QRR also, okay, in terms of IRM and di by dt. These expressions are valid only for fast recovery diodes, okay. So as long as this concept is considered, please, important expressions, okay, important expressions. One is QRR, expression for QRR is equal to area under the triangle, okay. So this expression is important. Area under the, it is simply the area under the triangle, okay. So if you successfully recall that characteristic, how the current is decreasing and which triangle we have considered actually, okay. So from that you can write QRR. Once we get QRR, next we can write the IRM in terms of di by dt. What is the IRM in terms of di by dt? Here it is. This is this is IRM is equal to TA into di by dt. IRM in terms of di by dt, okay. This expression. And if fast recovery diode is there, then these two expressions, this expression and this expression, these are important, right? Now let us discuss some numericals related to this. Okay, so here now we can again the same question they are asking. Blocking voltage is again the same. I am repeating. Blocking voltage is nothing but the voltage that can be blocked by the device. That is nothing but the blocking voltage, right? Okay. Next, and the blocking voltage and that breakdown voltage both are same, because you can check once the voltage across device becomes equal to that breakdown voltage, the breakdown of the junction takes place now. So device, you can check the diode can block how much voltage. Here the diode can block how much voltage from this point till this point, means diode can block this reverse VBR na. This so much voltage the diode can block. Yes or no? So the breakdown voltage and blocking voltage both are same, and your diode blocks the voltage during reverse bias only, okay, during reverse bias only, right? So this VBR is nothing but the blocking voltage, and that is nothing but your breakdown voltage again. Okay, next. Now let us discuss the numericals. Is this visible? Is it visible? Yes, no. Okay, let us discuss the numerical. A power diode has a reverse recovery time of 3 microseconds. So it is given TRR is equal to 3 microseconds and di by dt of 50 ampere per microsecond. Find the storage charge. Storage charge means what? It is a QRR. Storage charge means QRR we need to find. Okay, so let us first note the data. TRR is equal to 3 microseconds. So it is a 3 into 10 to the power minus 6 seconds. Next, di by dt is given. It is equal to 50 ampere per microsecond, which can be written as 50 upon 10 to the power minus 6 ampere per second. Okay, 50 upon 10 to the power minus 6 ampere per second. Our task is to find the storage charge. Storage charge is equal to QRR. We need to find the QRR, right? So now you can check here whether the softness factor they have given. No, right? TA not given, TB also not given. Okay, so simply here we need to assume TRR is equal to TA. Here we need to consider TRR is equal to TA. Okay, otherwise we cannot solve this example. Okay, so TRR is equal to TA. Yes. So as, let me write, softness factor TA, TB not given. So therefore assume fast recovery diode. Fast recovery diode. So therefore TRR is equal to TA only na, in fast recovery diode, right? TB is very small. So now from this our task is to find now QRR. What is QRR? QR is equal to area under the triangle, which is equal to 1/2 into IREM, okay, into TRR. Okay, but TRR is equal to TA, right? So we can write it as now QRR, that is the storage charge, okay, is equal to 1/2 into IREM into TRR, right, into TRR. Instead of TRR we can put the TA. Okay, instead of TRR we can put the TA. Now you can check here. Yes, here di by dt is given. Di by dt is given and TRR we assume that it is equal to TA. So can we find IREM? Yes. Now IRM is equal to what we have written? It is equal to di by dt into TA na, di by dt into TA. So let me write it as, which is equal to di by dt into TRR. What is the di by dt they have given? It is a 50 upon 10 to the power minus 6 and TRR is 3 into 10 to the power minus 6. So it is a 50 upon 10 to the power minus 6 and 3 into 10 to the power minus 6. So from this we can find IREM. Minus 6 cancel out. So it is equal to 150 ampere. This is the IREM. This is the IREM. Now we know IREM. Now we know TRR. So can we find QRR? So therefore QRR is equal to, yes, QRR 1/2 into IREM into TRR. So which is equal to 1/2 into 150 into TRR is 3 into 10 to the power minus 6. So you can check it is equal to 75 into 3. So it is a 225 microcoulomb, right? This is a QRR, reverse recovery charge, that is a storage charge. Correct? This is a storage charge. 225 microcoulomb. Okay. Next, let us discuss the next example. The reverse recovery time of a diode is TRR is equal to 6 microsecond, and the rate of fall of diode current is di by dt is equal to 10 ampere per microsecond. If the softness factor is 0.5, so yes is given. Calculate the storage charge QRR and the peak inverse current IRM. So now we need to find the QRR and the IRM. Yes, please solve. TRR is given 6 into 10 to the power minus 6 seconds. Di by dt is given 10 ampere per microsecond, which is, I can write it as a 10 upon 10 to the power minus 6 seconds, ampere per second. It is an ampere per second. Okay. Next, S is given. It is equal to 0.5. S is a 0.5. Our task is to find QRR and IRM right? So in order to find IRM, we require a di by dt and TA. Na? Di by dt is given. TA we need to find. And in order to find QRR, we require IRM and TRR. TRR is we know. IRM we need to find. Okay. So first, S is equal to, we know it is a TA plus TB. Na? Sorry, S is equal to TB upon TA. Just a minute. Yes. Yeah. So here S is equal to TB upon TA. S is equal to TB upon TA. Right? So now here we can write therefore 0.5 is equal to TB upon TA. Okay. So therefore what is TB? TB is equal to 0.5 into TA. Right? TB is equal to 0.5 into TA. Now we know TRR also. TRR is equal to what? TA plus TB. TA plus TB. Okay. So can we write it is equal to TA plus 0.5 TA. 0.5 into TA. So it is equal to 1.5 into TA. This is your TRR. Now you can check TRR, we know it is a 6 microsecond. Okay. So therefore 6 into 10 to the power minus 6 is equal to 1.5 into TA. So if you check, therefore TA is equal to 6 micro divided by 1.5. So it will be roughly 4 microsecond. 4 into 10 to the power minus 6 seconds. This is a TA. This is a TA we are having, right? Now, so TA is 4 microsecond. Now TA we know di by dt. So can we find IRM? Yes. So therefore IRM is equal to di by dt into, it is a TA. Di by dt is given 10 divided by 10 to the power minus 6. So it is a 10 upon 10 to the power minus 6 into TA. It is a 4 into 10 to the power minus 6. So minus 6 cancel out. So it is a 40 ampere. This is a IRM. Right? IRM is 40. Now IRM we know TRR. Can we find QRR? Yes. So therefore QRR 1/2 into, yes, it is a TRR into IRM. Right? So it is equal to 1/2 into, what is TRR? 6 microsecond, right? So it is a 6 into 10 to the power minus 6 into 40. Okay. So it will be 120 microcoulomb. 120 microcoulomb, right? This is the QRR, 120 microcoulomb. Right? Sharath, how it is a 600 micro? Okay, yes. So simple examples, this type of examples they have asked in the previous GATE ESC examinations, right? You can check. Last example we will discuss, and next will be moving towards the thyristor, that is the SCR. Okay, so most famous device. Next, let us discuss this numerical. For a power diode, TRR is 3 microsecond and rate of diode current decay is 50 ampere per microsecond. That is the di by dt is given. For a softness factor of 0.3, find the peak inverse current and storage charge. Same, right? Whatever just now we discussed, na? The same procedure we need to follow. You can check, and this will be the homework for you. Okay. Next, now let us discuss some additional points or the theoretical points related to the power diode. So basically, there are three types of the power diodes. One is the general purpose diode, second one is the fast recovery diode, and third one is the silicon carbide diode. Out of that, the silicon carbide diode is not it is a commercialized yet, due to it is having some thermal stability issues. Okay, so let's discuss the general purpose diodes. General purpose diodes are the diodes which are having the voltage rating of 6000 volt and 4500 kilo ampere, right? Market available diodes. For these diodes, generally the TRR, that is the reverse recovery time, is in the range of 25 microsecond. Okay, 25 microsecond, which is a high, I am saying. Okay, 25 microsecond is a high time, because we are having the diodes which are having the TRR, it is in the range of nanosecond even. Okay, next. So these diodes are generally used in the rectifier circuitries as a freewheeling diodes. Okay, so fast recovery diodes. Next one is the fast recovery diodes. These diodes are available in the voltage range of 3000 volt and 1 kilo ampere, 1000 ampere. Okay, the TRR is comparatively lesser than that of the general purpose diodes. It is in the range of 0.1 microsecond. For general purpose, it is a 25. For fast recovery diodes, it is a 0.1 microsecond. These diodes are generally used in the inverter circuitries and the chopper circuitries, or the commutation circuitries of the SCR and the SMPS also. You can check, compared to the rectifier circuitry. Okay, we require a fast switching devices in the choppers, in the inverters. Okay, because in the inverter, if you look in the inverter, the output voltage frequency is in kilohertz. So if you take the output frequency is kilohertz, so what is the switching time required, right? It is 1 divided by that kilohertz time. Okay, so very less time is required. Very fastest switches were required in the inverter. So that's why generally the MOSFETs are preferred in the inverters. But these diode, fast recovery diodes, where these diodes are used in the inverter circuitry, these diodes are used as a feedback diodes. These diodes are used as a feedback diodes. Okay. Whereas in the rectifier circuitry, if you check, in the rectifier, rectifier is a AC to DC converter. Na? In India, is the available frequency for the AC supply is 50 hertz. So we are having only 50 hertz input. Na? So you can check 50 hertz input we are having. So required switching frequency comparatively is very less, because one cycle time, right? One cycle time for the sinusoidal is a 10 millisecond. Whereas if you check in the case of inverter, as I said, the output frequency is in kilohertz. So what is the one half cycle time? It is that 1 divided by that kilohertz frequency. Okay. So 2 divided by that, 1 divided by 2 times that kilohertz frequency. So that's why it is a very high switching rate is required in the case of inverter or the chopper circuitry. But whereas in the rectifier circuitry, lesser switching time diodes are also sufficient. Okay, means the diodes which are having the more TRR, those are also can be used in the rectifier circuitry. But those diodes we cannot use in the inverter circuitry. Okay. Next, we are having the silicon carbide diode. Strictly speaking, the silicon carbide diode are having a very high breakdown voltage and ultra fast switching speed. Ultra fast switching speed means what? It is in the range of nanosecond. In range of nanosecond. Range of nanosecond. Okay, but due to the thermal stability issue, these diodes are not generally used. Okay, yet these diodes are not commercialized, but we don't know. Currently they are doing the research, and probably maybe after some years these diodes we can be seeing in the market, okay, as a commercialized. Next, so this is about the types of the power diodes, right? Types of the power diodes. Only theoretical bit, please go through it once, okay? Sometimes they have asked the question. Sometimes they ask questions like the rating of the voltage and current rating of the general purpose diode is. What is the range of TRR for the general purpose diode is? Okay, and it's probably, if you suppose they give the options like general purpose diode, fast recovery diode, silicon carbide diode. Out of these, which diode is the fastest diode? Okay, or which of the following is the fastest diode? And like this type of questions they will ask, or they may ask the general purpose diodes are used in, right, in which circuitry? But they will give the option in a rectifier as a freewheeling diode. Okay, they may give the option as a chopper circuitry, commutation circuitry, etc. Okay, like this they ask the question. Okay, sir, what is mean by freewheeling diode? Okay, Dwarkesh, that you will understand while discussing the rectifier circuitry, because in the rectifier we're having the load is RL, and across the RL load generally we connect to one diode, that is nothing but the freewheeling diode. The actually purpose of that freewheeling diode is to provide the path for the inductor, to release the energy, right? So yes, what is the symbolic representation? Symbolic representation for all the three is the same. Okay, simple diode, anode, cathode, and that shape we are having, right? Same symbols. There is no change in the symbols. Yes, just now I told you how which type of questions you will be getting, right? Among them, which is best? Actually, strictly speaking, the best is silicon carbide diode, but it is having some problem, na? Right? Because it is the fastest device we are having, silicon carbide diode.
Sir, can you
yes?
please show the homework problem once for a few seconds?
Just a minute. Yes. You can note the data: TRR 3.9 micro, di by dt 50 ampere per micro, and softness factor 0.3. The things we require to find are IRM and QRR. Okay. Next, types of power diodes we discussed. The last point regarding the power diode, the power diode specifications. Suppose if we want to select the diode for a particular application, then which things we need to check, okay, and how to select the diode, right? That we are going to discuss now. So during the selection of power diode, the following specifications considered. First one is the average forward current. Average forward current means what? Suppose I want to use the diode for a particular application. Okay, let me suppose show here. Suppose I am one circuitry here, it is a AC supply. Suppose the diode is here. Okay, and let me consider it as a, suppose the motor is here. Okay, motor. Consider this is a DC motor, or you may consider the induction motor. Okay, doesn't matter. Right. So now here from this, yes, if I want to use the diode in this circuitry, then the average forward current means what? It is the average load current, because diode is connected in series with the load. Na? The load is nothing but, in this case, it is a motor. Okay, so average forward current is nothing but the average load current. Average forward current is nothing but average load current. Average load current. So how to find the average load current? For that, we need to draw the waveform. Okay, and we need to find the I average. That you will understand. This is like a simple your single phase half wave uncontrolled rectifier circuitry. Okay. So we need to check first of all the circuit average current, that is nothing but the load average current, and that for the which diode is suitable for that current rating, that we need to select. Okay, right? So this is the average load current. Next, reverse blocking voltage, that is the PIV rating, peak inverse voltage. Now here again the word is blocking. Here again the word is blocking. Okay, so now you can check here when the supply voltage is negative. When supply voltage is negative, it is like a polarity minus here and plus here. So this minus will be at the anode of a diode. This plus will appear at the cathode of a diode. So it is like when supply voltage is negative, diode will be in the reverse bias mode, right? So when diode is in a reverse bias mode, whatever the supply, because we know diode voltage is like, it is like a VD. Okay. So now you can check when supply voltage is negative means minus here plus here, right? And when diode is in a reverse bias mode, current in the circuit will be 0. Okay. So when the current in the circuit is 0, you can apply the KVL to this loop. It is a plus VD plus VS is equal to 0. Okay, because the diode is acting as an open circuit, so that's why current flowing through the load will be 0. If the current flowing through the load is 0, your voltage across the load will be 0. Okay, so therefore we can write it as a plus VD plus VS is equal to 0. So therefore you can write VD is equal to minus VS. VD is equal to minus VS. So now VD is negative. VD is negative means voltage across diode is negative. And what is the peak value of that negative voltage? Whether VS is our constant voltage? No. VS is a sinusoidal voltage, na? So as the VS is sinusoidal voltage, whatever the peak value of that sinusoidal voltage, that will be like your, yes, peak inverse voltage for the diode, PIV rating for the diode. Okay. Same thing you will understand while discussing the rectifier circuitry again. Okay. So here the PIV for our case, PIV of diode in our case, it is equal to V max, because in this here we are having the peak inverse term is there, na? So that's why generally PIV, while writing the PIV, we need to write only magnitude, right? Not the sign. Okay, sign is not required, only magnitude, because here term inverse is already present. Okay, so means for this case, if I want to select the diode which is having the PIV, yes, we need to go for the VM, right? VM. And what is the VM? That depends on your supply voltage magnitude again. Okay, right? In whatever the single phase supply we are having, right, which we are getting from electricity board, it is having the RMS value 230, na? So peak value will be 230 into root 2. So that why it will be roughly 325.27 something. Okay, so PIV will be that much. Next, conduction drop. Conduction drop means conduction drop across the diode. While selecting the diode, we need to go for the data sheet of the diode. Okay, and from that we need to select the diode which is matching, okay, to this average forward current, which is having this PIV rating, and the diode which is having the less conduction drop. Okay, that we prefer, because conduction loss means what? Basically it is a loss, na? Conduction drop is nothing but the voltage drop across the diode, and related to that conduction drop we are having the conduction loss also, right? So generally we try to minimize the conduction loss, right? Generally we try to minimize the conduction loss. Okay, because it is a wastage of power. Conduction loss means wastage of power, because ultimately diode is a switch. What we expect, our switch should, yes, act as an ideal switch. This is our expectation actually, but in practical case we are not getting the ideal switches, na? That's why these switches are having some voltage drop. These switches are having some limitation like a voltage blocking capacity, current carrying capacity, right? These switches are having the some power loss, right? So in addition, the practical switches are having the limitation like switching time, right? That is the switching frequency and those things. Okay, next, so conduction drop, this is the one specification we need to check while selecting the diode. Next, TRR, it will decide the switching speed. TRR means reverse recovery time. Just now we discussed what is the TRR. Okay, so we need to select the diode which is having a suitable reverse recovery time. Okay, suitable reverse recovery time. Next, so So you can check for this application. If we want to check for this diode, what is the required TRR, minimum TRR? When Vs is positive, diode will be in the forward bias mode. So diode will be in the conduction mode. When Vs is negative, when Vs is negative, you can check diode is in an off state. We're having supply voltage, it is like this. Vm into sine of omega t, right? This is sinusoidal supply. It is like a pi here, it is a 2 pi here. Suppose we are having a supply frequency is 50 hertz. Supply frequency is 50 hertz. Then, yes, at this instant our diode will turn on. Na? As soon as the supply voltage becomes positive, our diode will turn on. Means from this point to this point, yes, our diode is in an on state. You can check. Diode is in an on state. Now at pi, yes, after pi supply voltage negative, so diode will be in the reverse bias mode. So diode will turn off. So you can check here from pi till 2 pi. From pi till 2 pi. Yes, there is a no functioning of the diode, right? So while selecting the TRR, we need to select the diode such that the diode should be getting successfully turned off within this time. Within this time. If diode's TRR is greater than this time, we cannot select that diode here for this application, right? Because diode will be in the off state only during this condition. Okay. So during this only during this time. So during this time, our diode should be successfully turning off. Okay. Then so for 50 hertz frequency, what is this time? One cycle time is like a 1 by 50 na. So it is equal to 20 milliseconds. So what is the time corresponding to this half cycle? 10 milliseconds. 10 milliseconds. Are you getting the point? Means to turn off, in order to successfully turn off, successful turn off means for neutralizing the additional charge carriers, right? Neutralization of the additional charge carriers. Those were getting added into the N minus layer, right? When device was in the conduction mode due to the conductivity modulation. Okay. So diode is getting this much time to remove those charge carriers. So we need to select the diode which is having the TRR, yes, that should be less than this 10 millisecond. That diode we can prefer for this application. Okay, but whereas if you check for the inverter, as I said in the inverter, this frequency, this is for rectifier, na? Input is AC, so available frequency is 50 hertz. But whereas for inverter, the available frequency or the output frequency is in kilohertz, na? Right? Let us consider it is equal to, let me consider the minimum, that is 100 kilohertz. We are having the inverter circuitry which are having, which requires the output frequency 100 kilohertz even. Okay, but suppose this is a 10 kilohertz. So if the switching frequency is 10 kilohertz for the inverter circuitry, what is the time corresponding to one cycle? Time for one cycle. Time for one cycle, yes, is equal to 1 by 10 k na? So it is equal to 0.1 millisecond, na? 0.1 millisecond. This is the time corresponding to one cycle. Okay. So out of that one millisecond, our diode will be in the on state for some time. Na? So therefore, we need to select the TRR. We need to select the TRR that should be less than, okay, yes, almost 50% of this time. That is equal to your 0.05 millisecond. So that's why you can check TRR required here and TRR required here. Here 10 millisecond is sufficiently high time, but whereas here 0.05 millisecond is a very less time. So we require a fastest diode, fast recovery diodes, okay, in inverter case. But whereas in the case of rectifier, yes, the diode which is having a sufficient TRR that can do the job. Okay. Next, thermal impedance. The thermal impedance of the day. What is the thermal impedance and those things you will understand while discussing the thermal modeling. Okay. Actually, for any semiconductor device, as the semiconducting devices are very sensitive to the change in the temperature. Why the device temperature is changing? Because the heat is generating. Why the heat is generating? Because the power loss is taking place. Why the power loss is taking place? Because of the, yes, resistance offered by the device or its equivalent modeling, right? Because we are having the practical devices, definitely those will be having some on-state resistance and those things. Okay. So due to that, some power loss will be taking place. Due to that power loss, yes, our devices will be having the heat generation, power loss in terms of the heat. due to the heat, temperature will be increased. Okay, so therefore we require the devices, the diode. Okay, diode's thermal impedance value is also we require. Okay, next to design the heat sink. Next, remaining two are the surge current and the I2T rating. What is the surge current? The surge current is required to design the short circuit protection equipment. Short circuit protection equipment means, suppose if I am using this diode, okay, for a particular application, right? So definitely we need to provide the protection to our devices. If you check our SCR, for the SCR we need to protect total, I think, eight protections we need to provide the SCR. SCR is a very small device, but we need to protect it because that is a very important device. Similarly, each power electronic device, each power electronic switch plays a important role, plays a unique role in that circuitry. So if our power electronic switch does not perform what we expect, okay, in that way, then it will directly affect on the output of the circuitry. Okay, and if you check in the bigger plants, in the bigger industry, if our one of the power electronic switch fails to operate, then directly it will affect on the production of that industry. So that's why these devices are very, very important. So that's why you need to protect the devices. Okay, and the next two are the surge current and the I2T ratings. These are the required for designing the short circuit protection of the for the equipments. Okay, short circuit protection for the devices. So what is the surge current? The surge current is nothing but that is a transient current. It is a non-repetitive actually. Okay, it is a transient current that the device can withstand safely, right? The transient current that the device can withstand safely. Okay, now suppose in this case, suppose we are having this circuitry, this DC motor we are having. As we know, in the DC motor, the starting current is high because the back EMF is less. Yes or no? Because at start the motor is stationary. Okay, and as the motor is stationary at the starting, the motor is a stationary. Due to that, the speed is a zero. The speed is zero means back EMF is zero. The back EMF is zero is nothing but the motor draws a high current. So in order to avoid that, generally we connect the starters. Yes or no? We're having a 3-point starter, we're having a 4-point starter, etc. In the case of DC motor. Similarly, in the case of induction motor, we're having the star delta starter, we're having the auto transformer starter, etc. Right? So suppose for this DC motor, the starter is not working. Okay, starter is having some fault and this starter is not working. So due to that, what will happen? At the starting purpose, this motor will draw more current. And how, through which circuit this starting current of the motor will be flowing? Yes, in this same circuit na. So whatever the starting current of the motor, the same current will be flowing through the diode also, right? But whether the starting current is for all the time, that will be present in the circuit? No, starting current will be present only for the starting time na, right? So that's why it is a that current is present only for the very small time. So that's why it is a transient current. That's why it is known as a transient current. Okay, and that to that transient current also our device should withstand. Our device should withstand. That is nothing but your surge current. Okay, that is the surge current. Okay, next, surge current is not your normal operating current. Please be careful. Surge current is a it is a non-repetitive current actually, and it will be there in the circuit for a very short time interval. Okay, generally if you check the specification, sheet of the device, generally the surge current rating is specified like, generally the surge current rating is specified like in this way. Let me write here. It will be 300 ampere for 10 millisecond. Okay, or it may be like some ampere for 8 millisecond. Like this, they specify the surge current rating. So what it indicates? For 10 millisecond, yes, for 10 millisecond, if this surge current means our diode can withstand with this much of current for a 10 millisecond, for this much of current for 10 millisecond. That is the meaning of this term. Okay, that is the meaning, right? Next. So why this is 10 millisecond and 8 millisecond? The 10 millisecond is the, you can check that for the frequency of 50 hertz, the 10 millisecond time is corresponding to the half cycle time. Okay, and the surge current will be there at maximum for half cycle only. Okay, so that's why it is given as a 10 millisecond, and 8 millisecond is for a frequency of 60 hertz. You can check if the frequency is 60 hertz, then the time corresponding to the half cycle is 8 millisecond. Okay, so that's why generally they specify it in terms of 10 millisecond and 8 millisecond. Okay, so this is a surge current. Next, I square T rating. I square T rating. When the surge current is flowing through the diode, when the surge current is flowing through the diode, then our diode absorbs some energy. Diode absorbs some energy. Okay, so therefore you can check the I square T rating is required. It specifies the amount of energy that the device can absorb for a short period before fault is cleared. Okay, so this much of, if I square T rating of a diode, let us consider it as a X, then the meaning is that diode can withstand, okay, with a surge current energy, okay, or I square T rating, or the energy absorbed by the device will be this much. Like this, they give the on the specification sheet or the data sheet of the device. Okay, so these are the specifications which we need to go through while selecting the diode for a particular application. Okay, so it is not like that I am going to design a rectifier and I am selecting arbitrary any diode, randomly I am selecting any diode. It is not that much easy. Okay, we need to select, we need to first of all think about the circuitry in which we are going to use that diode. Okay, and after that once we get that circuitry, whatever the maximum current, whatever the maximum inverse voltage, what is the average current, right, what is the possible surge current, right, after those values we can go for the selection of the diode, right? So this is about the diode. During fault heavy current flows. Yeah, during fault heavy current flows means that is what we discussed. Okay, because diodes should withstand, because fault current means what? Anyways, in an electrical circuit, if the fault occurs, we are having the protecting equipments, na? And those protecting equipments are having some response time, na? So therefore, in this case, if you check, the surge current is nothing but that will be considered into your fault current also, right? Because fault current will be there only for a very short time period. Okay. Why we consider voltage across motor is 0? You can check, na. DC motor we are having, and in the DC motor we know back EMF is proportional to the speed. At the starting, the speed is 0, na, so back EMF will be 0, right? Sir, explain average charging current, average forward current. Average forward current means, suppose here we're having the DC motor, or simple way you can replace this. Simple way you can replace this DC motor with a resistor. For example, suppose if I am having the circuit like this, I want to connect the device. This is a diode. Suppose here is the resistor, and here it is a supply voltage. Suppose supply voltage is 230 volt RMS. This is a diode D, and suppose this resistor value is 25 ohm, for example. Okay, so how to find the average forward current? You can check here, supply voltage will be Vm sin omega t. So it is having a positive cycle, negative cycle, positive cycle. This is a Vs 0 to pi, pi to 2 pi. Okay, so next, how will be the nature of the current flowing through the diode? That is the current in the circuit. During positive half cycle, diode will be in the on state. Okay, so current in the circuit will be like this. This is the omega t 0. So this is the current flowing through the diode. Yes or no? After that it will be 0, and again the same. Now you can check this current when diode is in an on state. The voltage across load is same as that of your supply voltage. Now when Vs positive, it is a plus here, minus here. Diode will be in the conduction mode, so V0 is equal to Vs. Okay, same analysis we are going to do, okay, in the rectifier circuitry. Okay, so only time being, please try to understand V0 is equal to Vs when diode is in a conduction mode. So if V0 is equal to Vs, V0 is equal to Vs, this is during omega t is equal to 0 to pi. Omega t is equal to 0 to pi. Okay, so diode is in a conduction mode. So V0 is equal to Vs. Vs is this, like this we are having. Okay, so therefore V0 also this type of shape will be getting, and the load is resistive now. So therefore what about the I0? According to Ohm's law, I0 is equal to V0 by R. but V0 is Vs, so it is a Vs by R. So if we are having Vs is this type of waveform for 0 to pi, and if I divide this waveform with the R, that is a 25. So what will be the nature of my current I? Current nature will be like this, na? When supply voltage is maximum, definitely your I0 will be at a maximum value. Definitely the magnitude will be different, but nature will be same, na? Right? So this will be the nature of your current. Okay. And what is its peak value? Its peak value will be peak value of the supply voltage divided by the resistance value. What is the peak value of the supply voltage? For sinusoidal supply, by default for AC supply or in AC circuit, by default whatever the value given is your RMS value only, right? So this is your RMS, Vs RMS value of supply voltage. So if this is RMS for sinusoidal, so what is the peak value? So peak value is equal to RMS into root 2, na? For any sinusoidal we know peak value is equal to RMS into root 2. So if you check, it is roughly 325.27 volt. This is your V peak, na? Peak value of the supply voltage. So if this is 325.27, then what about this peak value? This peak value is 325.27 divided by 25, right? So divided by 25 means it is like 12, right? 12.1, I think, right? 12.1. Sorry, 13 ampere, right? It is a 13 ampere, correct? So this is the peak value. Now can we find the average value? Average forward current means what? Average value of this current. Okay, so I average. Now we need to find for this. We already discussed, na? What is the I average? It is a Im by pi, na? For this type of circuit. Or how to find is equal to 1 by, this is a 2 pi, na? After 2 pi again the same cycle repeats, here positive and again 0. Okay, so it is like a 1 by 2 pi integration from 0 to pi. It is like a 13 is the peak value. So it is a Im into sine of omega t into d omega t, right? So we can write it as is equal to Im by 2 pi, okay, into integration of sine is minus cos of omega t, limit 0 to pi. You can put the limit 2 will be getting cancelled and it is Im by pi. Im is 13 divided by pi, right? So from this we can find, okay? So that will be your average circuit current, that is the load current, that will be equal to your average forward current that is flowing through the diode, because current in the diode is same as that of your load current only. Is this clear? Right? So accordingly we need to select the diode current rating. Here we have considered a very small voltage and very high resistance, but in practical case, okay, if you check the circuit like your battery charging circuit type, okay, you'll be getting a very high current there. Okay, so right, so this is about the diode. Next, okay, silicon SCR we are having, it's 845. Okay, we'll stop here. Tomorrow we'll start fresh the SCR, silicon controlled rectifier. Okay, till time if you are having any doubt, please ask.
Hello, sir.
Yes, please.
Sir, in a unipolar switch.
Unipolar switch, huh? Yes,
sir,
audible. Please go ahead. You are
for
audible.
BJT, you have shown like it is voltage.
It is.
Hello, am I audible, sir?
Yes, please.
Sir, in unipolar switch, you have shown that BJT is blocking positive voltage.
Yes.
Then why it will not block negative voltage, sir?
That you will understand while discussing the BJT. Okay. Till time
Means you
being,
will
please
discuss
consider
about that.
whatever I have given as it is. When we discuss, because yet we have not discussed na BJT, MOSFET, IGBT, GTO, etc. Anything we have not discussed. Okay.
Okay, sir.
The only to cover those type of questions. So that's why I summarized there. Okay.
Okay, sir. Another doubt is SOA is there, na, sir? SOA.
Yes.
SOA stands for static operation, means safe operation area or static operating area.
It is a safe operating area.
Means one day you said like static, another day you said safe operating. safe
No, no, no,
operating area is
safe
correct, sir.
operating, safe operating area.
Okay, sir. And one more thing is, you have given specifications for a power diode, na sir? General purpose
I
diode,
have
fast
given
recovery diode.
specification. Yes, yes. This is here only. Huh?
In that, V is equal to 6,000 volts, I is equal to 4,500 amps you have given, na sir?
Okay, general
Previous
purpose
slide.
diode. Yes, yes. Huh.
That V stands for means reverse voltage, na sir? How much reverse voltage
Yes,
it can
yes.
block?
How much reverse voltage it can block? In the case
For-
of diode, it is only reverse voltage because diode blocks only reverse voltage.
Yes, sir.
But now when we discuss about the thyristor tomorrow,
Okay,
you
sir.
will understand that thyristor blocks the forward voltage as well.
Yes, sir. Yes, sir.
Okay, in the case of diode, it is only reverse voltage.
Okay, sir. That's it, sir. Thank you, sir.
Okay. Okay.
Hello, sir.
Yes, please.
Sir, how we can say uncontrolled switch is passive switch, sir?
Uncontrolled switches.
Passive switch.
Actually, the thing is uncontrolled. We as these are not controlled switches, na, so that's why these are the passive switches. We cannot control it. Yes or no?
Okay, okay, sir.
They will be in the on state only when the forward voltage will appear across that diode.
Okay.
I cannot control. Who is controlling? Your supply voltage is actually indirectly controlling.
Okay, okay, sir. Okay, thank you.
Right? Right? Okay. Okay.
Yes, sir.
Next. Yes, please.
Sir, will you please explain the characteristics of diode?
Which characteristic?
Turn off characteristics. Sir.
Turn off characteristic. Just a minute. Yes. Yes, this one.
Yes,
Shall
sir.
I reduce some percentage here?
Yes, sir. Yes.
Just a minute. Don't know why sometimes it is not. Yesterday's notes I have uploaded. Okay, I think you might have got it. Just a minute. Okay, yes. In this,
Sir, from this initiated turn off of diode, from this instance, sir, please.
okay, you want me to explain again? Okay, yes.
Yes.
Please check. From 0 till this instant, our diode is in an on state.
Yes, sir.
So therefore, current from the diode is high, voltage across diode is very small. That is the on state voltage drop, right?
Yes.
At this instant, now we have initiated turning off of a diode. Okay. So for that, we have maintained the reverse voltage. Means indirectly what I have done, at this instant, I have maintained the reverse voltage across the diode. So we expect that diode should immediately block that voltage. But in the diode, it is not happening. Why? The reason is, if you check, the reason is because the depletion layer is not available. If the device is in a conduction mode, whether the depletion layer is present, no, right? So that's why we need to the process. What is the process to build the depletion layer in the device? That is nothing but from this point to this point, whatever the characteristic we are having now, that characteristic it indicates. Now, why the depletion layer building is taking time? Because when device is in the conduction mode, at that time you can check at in the construction we are having P plus layer, N minus layer, and N plus layer. As device is in a conduction mode, the junction across depletion layer width across the junction is 0. So it is like device is acting as a short circuit. So due to that, what is happening? We are having the N minus layer, its width is more. N minus layer is there, its width is more, very high width. But there the number of charges are very less, right? So due to that, what will happen when the device is in the conduction mode, the heavily doped devices, heavily doped layers we are having, that is the P plus and the N plus. As these two layers are having very less width, but the number of charge carriers there is very high now. So once the depletion layer is depletion layer width becomes 0, that is when device is in a conduction mode, the positive charge carriers from the P type layer, that is a P plus layer, and negative charge carriers from the N plus layer, these charge carriers will be entering into that N minus layer. Okay, due to that external supply means whatever the supply voltage we have maintained, right? So that's why when device is in a conduction mode, we will be having into the N minus layer added charge carriers will be present there. So now, due to those added charge carriers, our device is taking time to block that reverse voltage. So now if I apply the reverse voltage at this point, the current flowing through the device will not become suddenly zero. First of all, from this value till this negative peak, okay, it will be decreasing like this. Current will decrease, reaches zero, and after that it will be going into the negative value. Why it is going into the negative value? Because, and it is a reverse current, na? Because whatever the added charge carriers are there, na, right? These charge carriers were getting neutralized. Neutralized means what? One positive charge, one negative charge. When they recombine, they will be getting neutralized. Okay, so like this, almost when 60% of the charge carriers getting neutralized, after that again current is decreasing. Try to keep it in mind. Current means what? Rate of flow of charges. If very large number of, initially suppose 1000 number of charge carriers are present, which are getting added into the n minus layer, all of a sudden all the 1000 charge carriers will try to, yes, getting neutralized. So rate of flow of charges will be high, na? So that's why current is increasing. Suppose out of the 1000, let us consider only 400 charge carriers are remaining now. 400 or 300, let us consider. So now if only 400 or 300 charge carriers are remaining there, so what is the rate of flow of charges for the neutralization? Comparatively less, na? So that's why current is decreasing. Okay. And when this current becomes equal to, okay, 25% of this peak value, okay, 25% of this peak value, at this instant you can check, it is like our diode is now ready to block that voltage. Our diode is now ready to block the voltage, right?
Yes, sir. Sir, what is this VRM?
This VRM is nothing but the reverse voltage. Actually, the thing is, it is expected that after this point only the voltage across diode should be negative.
Yes,
because we have maintained the reverse voltage, na? But the thing is, from here to here, diode is in the conduction mode only, because the charges are getting neutralized. Once the 60% of the charges getting neutralized, after that the voltage is reducing, right? And that voltage is having this negative peak. This is due to the stray inductance of the device, right? Stray inductance means it is again, it depends on the construction of the device. Okay, there is one term in the device or in the semiconductor, that is the stray inductance. Due to that the current is here, due to that the voltage is increasing, okay, and again it will be decreasing. Means actual diode is blocking the voltage, or voltage across the diode is increasing into the negative value after this instant, but diode is now ready for blocking the voltage is after this instant. Okay, after this instant, right?
Sir, sir, what is the stray inductance means actually?
Stray inductance means when we construct the device, right? At that time when we add the charges into the device structure, na, P plus, N plus, and the N minus layers. Due to that, it will be having the tendency to oppose the current. Okay, because we know the inductor is the element which is having the tendency to oppose the change in the current, right? So due to that, our charges are also having the tendency that to oppose the change in the current, that is change in their position actually. So due to that, there is a term like a stray inductance, means it is related to your rate of change of current actually.
Sir, means
Similarly, you can check when diode is in a reverse bias mode. When a diode is in a reverse bias mode, across that across the junction we're having a depletion layer present, na? And for the depletion layer, at one side we're having the layer of negative charges, and second side we're having the layer of positive charges. So when diode is in a reverse bias mode, at that time we're having one concept like a capacitance also. The capacitance concept, and here we're having the inductance concept. These two concepts we're having. Actually what we have done, what they have done, what they have done actually, they have simply characterized, okay, the device property in equivalent to that your inductor and the capacitor.
okay, sir. Sir, means due to this that inductance, this voltage drop is there VRM.
Yes. Due to that, but that inductance is not the external inductance. Let me tell you. This is in the device itself, due to its nature. It is not like we have connected the inductance into the device structure. No, due to the device property, that is behaving as an inductor. Okay.
Okay, sir.
Sir, hello.
Hi.
Sir, in the interval of TA.
In the interval of TA, yes.
Sir, can you say in terms of robots like discharge of charge, like recovery of charge, T and TB?
Yes, we can say na recovery of the charge. That's why it is a TRR, na?
So is there any classification between TA and TB in terms of charge?
Classification of TA and TB. Yes, just now I said the TA is corresponding to what? The neutralization of the charge. Recovery means what we are getting, whatever the charges are getting added, those charges were neutralizing. Na? So from corresponding to TA, almost 60% of the charges are getting neutralized.
Okay.
And after that, during TB, 40% of the remaining charges are getting neutralized.
Means total related to same thing like neutralizing. Means I think there should be like the charge recovery from junction to depletion layer to P and in depletion like that. There is no classification, sir.
No. Actually, charges recovery from N minus layer only. In the SCR, we're having the concept like charges recovery from the outer layers and the charges recovery from the inner layers, because SCR is a 4-layer device, na?
Yes, sir. From layer to layer and also to cooled depletion layer again. So from layer to layer one time and depletion layer to form like that. There is no classification.
Okay. Means in order to, you are saying that the first recovery of the charges and next one is the for the some charges for the formation of the depletion layer. Yes, you can say like that also. Yes, because here most of the charges will be getting neutralized, and from the remaining charges, okay, it is like a formation of the depletion layer, because unless and until the depletion layer is formed, our device will not be able to block the that voltage, na?
Yes.
Right.
Sir, one more doubt
At
is
this instant we can say our device depletion layer is now ready.
yes, sir. In the interval of TA, with the relation of V, sir. Actually, these are the dynamic characteristics of diode, right?
These are the highest, yes. This
Sir,
is during turn off.
can we relate these characteristics with static characteristics?
This characteristic with a static characteristic.
Yes, what I'm thinking is that in the interval of TA, current is negative, but voltage is positive. But in static characteristics, there is no point in that view.
Yes. No, you cannot do like that, right? Because static characteristic, when voltage is negative, it is like we are considering that the depletion layer is already present there. So that characteristic and this one, both are totally independent.
Okay.
Right? Okay.
Right. Sir, in minority charge carrier device, flow of current is only because of minorities or both minority and majority?
Only minorities.
Only minorities.
Yes.
Hello, sir.
Yes.
Hello, sir. Sir,
Yes.
I have, sir, in numerical one, sir.
Numerical number 1.
Yes, sir.
This one?
Like this one, sir, like that bidirectional unipolar in the numerical.
Just this one?
Yes, sir. If in this options, if you given diode, it is also answer.
If they would have given diode, na?
Yes.
Only diode.
Only diode.
No, diode blocks reverse voltage and allows only positive current. So for diode, yes, how is the static operating point location? It is here.
Positive and negative, second quadrant.
Right. Only.
Sir, but in the question he asked only one direction of and the another direction it is forward, right?
That is, I think, in second question. No?
Same question, sir. He given that the switch required to conduct only in one direction.
Conduct in only one direction, but required
so diode
to block
conducts
the
in
voltage,
forward direction. Right.
Required to block the voltage in both the direction, right? Both the polarities.
He given that like that.
Yeah, then the diode would be the answer, right?
Either means not both, sir. Either means.
Yeah. Either means both.
Any one is not right.
Either means what? This voltage as well as this voltage.
Okay.
Okay,
sir.
Yes.
Hello, sir.
Thank you, sir.
Yeah.
Sir, what is the difference between energy loss during transition and switching power loss, sir?
Energy loss during transition means switching loss and the conduction loss.
once showed in
Please
graph,
repeat
sir.
the question. Please repeat the question.
The difference in energy loss during transition and switching power loss, sir.
Switching power loss is actually the power loss during the transition period.
Okay, sir.
And you are saying the energy loss. Energy loss is the energy actually. Energy and power both are different things, na? Right? Switching loss, your transition period loss, both all are same. The only thing is whether they have asked the energy loss, whether they have asked the power loss. Okay.
Okay, sir.
So we have discussed the two types of the losses actually, switching loss and the conduction loss. Switching loss is only during the switching instant. Conduction loss is during the conduction period.
Operating period.
Right? Okay.
Hello,
And
sir.
Yes, one by one, please.
Yeah. Hello. Good evening, sir.
Good evening.
So, what is actually transient current, sir?
What is actually?
Transient current.
Okay.
We have
Transient.
discussed in surge current. also.
Just a minute. I will get it. Here it is. No?
It's a specification.
So suppose I am connecting their DC motor, for example.
Okay, sir.
Initially, motor is at the standstill position.
Yes, sir.
So back EMF will be like a 0 only.
Yes, sir.
So that's why motor will at starting motor will draw high current.
Okay.
And that high current is nothing but your transient and steady state. We are having the two states.
Oh, yes, sir.
In
Yes, sir.
control system,
Yes,
you might have studied.
yes,
Huh?
yes, sir.
Transient is very short period actually,
Yes, sir.
and steady state is your final state, right?
Yes, yes, sir.
In the same way, because when that current will be here high current, that will be only there during starting period, na?
Yes, sir.
Once
Yes, sir.
motor starts the speed, once motor gains the speed, after that the back EMF will be developed. So automatically the current will be decreasing, right?
Yes, yes, sir. So another one is what is conductivity modulation, sir?
Conductivity modulation means in this case, let me show. Yeah, power diode. Yes. This is the reverse bias. Yeah, this is a forward bias, right?
Yes,
So
sir.
suppose we are having a power diode. It is having a 3 layers, P plus, N plus, and N minus. Okay.
Yes.
When I purchase that diode from the market directly, definitely here we will be having the depletion layer.
Yes, sir.
At that time, this N minus layer will be having some charges. Those that will be the negative charges, and those are the lightly doped, na? Means
Yes,
lesser
sir.
number of
Yes.
negative charges, and the width of the volume will be very high. Okay. Once device starts conduction, what happens? Means it is
Charges
like
flow.
before conduction, it is like this N minus layer will be having some conductivity, na?
Yes, sir.
Once the device starts conduction, this P plus will add the positive charges, N plus will add the negative charges.
Negative charges.
So that into this N minus layer, charges will be getting added. Once the
sir.
charges getting added, what will happen? The conductivity of that N minus layer, it will be increasing, it will be improving.
Okay,
So that is
okay.
nothing but your conductivity
Conductivity
is
model.
changing. Na?
Yes, sir.
That's
Yes,
why
sir.
this is conductivity modulation.
Yeah, okay.
And due to that overall effect is conductivity is increasing, means resistivity is decreasing.
Yes, sir.
So that's why here in the minority charge carrier devices, we are having on state.
Hello.
I think sir disconnected.
Yes, yes.
Hello, hello, sir.